Hello, and welcome to the full course session on Physics Basics, your gateway to understanding the fundamental principles that govern the physical world. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're committed to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the foundational knowledge to excel in your academic or professional journey. Don't forget to subscribe to our channel for more insightful tutorials and updates on physics and other fundamental sciences. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll introduce you to the basics of physics, units, and measurements. You'll learn what physics is, how it relates to mathematics, and the scope of classical physics. We'll dive into the concept of units, who decides them, and the different types of units. We'll also cover scalar and vector quantities, exploring their differences in operations such as addition, subtraction, and multiplication by a number. In the second chapter, we'll explore motion, force, momentum, and torque. You'll learn the concepts of rest and motion, frames of reference, and the laws of motion. We'll also explain force, its type, and how it's measured. You'll understand the concepts of momentum and torque, including their units and vector properties. In the third chapter, we'll focus on work, power, and energy. You'll learn how to define and calculate work, energy, and power, along with the principle of conservation of mechanical energy and momentum. We'll dive into how these concepts are interconnected and their real-world applications. In the fourth chapter, we'll introduce you to heat, temperature, and electricity. You'll learn about the concepts of hot and cold bodies, temperature, and the zeroth law of thermodynamics. We'll discuss heat transfer, thermal conductivity, and resistance. In electricity, we'll cover electric current, current density, Ohm's law, and the types of materials based on their behavior in an electric field, including superconductors. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with Physics Basics.
Good morning, everyone. Today, we are going to start a Physics Basics course. On week 1, we are going to study about Introduction to Physics. The table of contents. The table of contents contains basically 3 things: Introduction to Physics, units and measurements, scalar and vector quantities. The learning objectives of the week 1 would be as following. The session will cover basic introduction to physics, units and measurements, deriving dimensional formula, scalar and vector quantities, addition and subtraction of vectors. Let's get started from introduction to physics. What is physics? Physics is understanding of nature and its laws. Physics identifies and reveals the fundamental laws that govern every event in nature. So, actually, physics is the study of nature. Relation between physics and mathematics. Physics is basically based on mathematics only. Or we can say that mathematics is the language of physics. Defining and explaining the laws of nature or physics without mathematics is really challenging, or we can say almost impossible. Moving to the next slide, physics is basically categorized into 2 levels. This has been done based on particle size and moving velocity. The categorization of physics has been named on classical physics and quantum physics. If the particle size is more than 10⁻⁻⁶ meters and the speed of the particle or the moving velocity of the particle is less than 10⁸ meter per second, then it comes under the classical physics category. Similarly, in the case particle size is less than 10⁻⁻⁶ meter and the moving velocity of the particle is greater than 10⁸ meter per second, then it comes under the category of quantum physics. The next thing we are going to study here today is units and measurements. Defining units. Units can be defined as a measure of quantity. It is a measuring standard of similar quantities. Like here we see an elephant and a cat. Both can be compared based on their weight. But do we know that how many times the weight of the elephant is higher than the weight of the cat? We don't, because we don't have the units. So, suppose there is a unit mass of for reference. Then we can say that an elephant and a cat can be compared for this purpose. Suppose the weight of the elephant is 200 times of the unit mass. Also, the weight of the cat is 2 times of the unit mass. Thus, we can compare both and say the weight of the elephant is actually 100 times more than the weight of the cat. Units are defined by the General Conference of Weight and Measures adopted by the International System of Units, that is SI unit. This has been done on an international agreement and it has been finalized on 1971. Basically, there are two types of units: fundamental units and derived units. Further, we are going to elaborate this. The fundamental units or base units. These units measure the fundamental quantities. Example, distance, temperature, time, etc. The fundamental quantities, they are dependent from one another. Let's revise all this. Fundamental units used to measure the fundamental quantities. And what are fundamental quantities? Fundamental quantities are independent from each other. Further, we are going to study about properties of fundamental units. The fundamental units basically should have two properties. The first property is invariability and the second one is availability. Let's get to know what's invariability and what's availability. Invariability. The unit must be defined as such. They are never changing. They are never changing, actually, I must say. Further, the availability is defined as the units must be easily accessible for comparison with other quantities. Next slide. The second kind of units that we have studied is derived units. It is possible to derive all the physical quantities from base quantities or fundamental quantities. As all physical quantities can be derived from base quantities, base units can be derived from all physical units. Example, speed, force, work, etc. How we can say that speed is derived? We know that speed equal to distance upon time, where distance and time both are fundamental units. Similarly, force. Force is defined as the mass into acceleration. We are going to study in future slides. What is measurements? Compares how much a physical quantity deviates from the reference of basic quantity is called measurement. There are basically 7 fundamental quantities and their corresponding units that has been represented by symbols. The 7 fundamental quantities has been given in the table. The first one is length. The fundamental quantity is length. The fundamental unit of length is meter. The symbol of meter fundamental quantity length is m. The second fundamental quantity is mass. The fundamental unit of mass is kilogram. The kilogram is represented by the symbol kg. The third fundamental quantity is time. The fundamental unit of time is second. The symbol of second is s. The fourth fundamental quantity is electric current. The fundamental unit of electric current is ampere. The symbol of ampere is capital A. The fifth fundamental quantity is thermodynamic temperature. The fundamental unit of thermodynamic temperature is Kelvin. Kelvin is represented by the symbol capital K. The sixth fundamental quantity is amount of substance. The fundamental unit of amount of substance is mole, and it has been represented by the symbol MOL, mole. The seventh and the last fundamental quantity is luminous intensity. The fundamental unit of luminous intensity is candela and is represented by the symbol CD. There are two supplementary units also included in the previous fundamental units. Those are plane angle and solid angle. The fundamental quantity plane angle as its fundamental unit is radian. The symbol of radian is RAD. The fundamental quantity solid angle has fundamental unit steradian and has been represented by symbol SR. There are also SI prefixes. Let's get to know them. What are SI prefixes? The physical quantities vary greatly in terms of their magnitude. Example, the mass of the earth is 6 into 10 power 24 kg. Similarly, if we talk about the mass of the electron, it's 9.1 into 10 power minus 31 kg. So, as I have told that the quantities vary greatly. The mass of the earth is 10 to the power 24 and mass of the electron is in terms of 10 power minus 31. So there is a very huge difference. Based on that, CGPM suggests representing the quantities in the power of 10. Let's see how it suggests. This is a table provided by the CGPM, and as I have told you, they have decided to fix it in the power of 10. Suppose 10 power 1 can be said as deca and represented by the symbol dA. Similarly, 10 power 2 has been represented by the symbol H and called as hecto. 10 power 3 is kilo and represented by the symbol K. 10 power 6 has been represented by the symbol capital M and called as mega. 10 power 9 is giga, represented by G. 10 power 12 is tera, represented by capital T. 10 power 15 represented by capital P and called as peta. 10 power 18 is exa and represented by symbol capital E. What's 10 power minus 1? 10 power minus 1 is deci, represented by symbol D. 10 power minus 2 is centi and represented by symbol C. 10 power minus 3 is milli and represented by symbol M. 10 power minus 6, it is called as micro, represented by symbol mu. 10 power minus 9, it's called as nano, represented by symbol N. 10 power minus 12, it's called as pico and represented by symbol P. 10 power minus 15, it's called as femto, represented by symbol F. 10 power minus 18, called as atto, it's represented by symbol A. So, exa, peta, tera, giga, mega, kilo, hecto, deca, deci, centis, these are all the prefixes. And E, P, T, G, M, K, these are respectively their symbols. Further, we are going to study about dimension. Quantities that are derived from base quantities are expressed as a product of different powers of base quantities. Like, for convenience, base quantities are represented by a letter. Like, example of these base quantities representation is mass, it is represented by M. Length, represented by L. Time, represented by T. Electric current, represented by I. Generally, these representations are in capital letters. Further, we are going to study formulating dimensions. Example 1. What is velocity? Velocity is equal to displacement upon time. So, the dimensional formula of speed would be, or dimensional formula of velocity would be Lt minus 1. Here L is representing the displacement, T is representing the time. And since we see that time is in the denominator, so the power of time here is minus 1. For understanding in another way, let's get to another example. What is density? Density is mass upon volume. So the dimensional formula of the density would be ml minus 3. Since mass is represented by capital M and volume is represented by cube of length. But since we see that volume is in the denominator of the formula of density, therefore there will be power of minus 3 with the L. Thus, the final dimensional formula of density would be ml minus 3. Let's get into the third thing of our week 1 course. It is scalar and vector quantities. What are scalar quantities? The scalar quantity is one that has magnitude of the quantity and it must be added as per the algebraic rules. For example, mass is a scalar quantity, temperature is a scalar quantity. How we can say that mass is a scalar quantity? Okay, let us get into that. Let mass of an object is A and has been represented by Ma equal to 5 kg and mass of the object B is Mb where Mb is equal to 4 kg. So sum of both masses would be Ma plus Mb, that is 5 kg plus 4 kg equal to 9 kg. Since both the masses have been added as per the algebraic rules, therefore mass is a scalar quantity. Similarly, temperature is also a scalar quantity. Let temperature of body A is Ta equal to 288 Kelvin. Also, let temperature of body B be Tb equal to 310 Kelvin. So, sum of both the temperature is Ta plus Tb, where Ta was 288 Kelvin and Tb was 310 Kelvin, which sums up to 598 Kelvin. Since both Ta and Tb both have been added with the use of algebraic rules, therefore temperature is a scalar quantity. What are vector quantities? Vector quantity. It is a physical quantity which represents both magnitude as well as direction. It is added as per the triangle rule of vector addition. This is a totally different rule which has not been covered in the general maths as of the algebraic rule. Let's get to know what is vector quantity with an example. Consider a person traveling from home to park, then to a shopping mall. So the vector from home to park would be, let's say, HP, and from park to shopping mall, the vector would be PM. So the resultant displacement would be HM. Note, the point to be noted here is vector HM is not equal to vector HP and vector PM. As the figure represents the vector quantities here, they cannot be added as an algebraic rule. So we need to have a new rule for vector addition called as triangle rule of vector addition. The triangle rule of vector addition, it is also called as parallelogram law of vector addition. Let's get to understand what is parallelogram law of vector addition. Let there be two forces acting on an object A. Here is the object A in the figure. So the force 1 acts on A in a horizontal direction, causing vector A. Here the force 1 is acting on A in a horizontal direction, called as vector A. Similarly, the force 2 acts on A with an angle phi, they call as vector B. Force 2 acting on a point A, object A, with an angle phi. This has been named as vector B. To know the resultant force acting on object A is, we need to have a formula. Thus, the resultant force is represented as vector AD square is equals to vector AB plus vector B whole square plus vector DE square. Let's get to know where this is in the figures. Vector AD, the diagonal represents vector AD and this is the resultant force. Vector AB is the force acting on the horizontal direction on object A. Vector B is here. Vector DE is here. So getting back into the formulas, vector AD square can be written as A plus B cos phi whole square plus B sin phi whole square. Let's get into this. Vector AB can be written as vector A. Similarly, vector BE. Here is vector BE. If this is angle phi, this is also angle phi, and vector B, therefore, by using trigonometry, can be written as cos phi, B cos phi. Again, we need to going to understand this in a better way. AC is vector B. So this is angle phi. So this would be also angle phi. Therefore, by using trigonometry rules, we can say that vector BE is equal to B cos phi. Further, vector DE can be represented in the same manner. Considering triangle D, B and E and applying trigonometry rules, DE can be written as B sin phi. B is again vector dB. Phi is the angle between point dB and DE. Thus, DE would be represented by B sine phi. Again, getting back into the formulas, AD would be written as A square plus B square plus 2AB cos phi to the power under root. This is called as the resultant force. So, getting ahead, the angle of vector A is alpha, and where to find out angle of the resultant force, we need to find tan of alpha. That would be dE upon AE. Let's see this in figure. The angle of resultant force can be represented by vector dE upon vector AE. Using trigonometry laws, we can say that d is b sine phi. AE is sum of AB plus BE. That is vector A plus B cos phi. That is what has been written here. So, tan alpha would be B sine phi upon A plus B cos phi. The next thing we are going to learn today is multiplication of vector with a constant. Let vector B equal to K into vector A, where vector B is general vector and it has been multiplied by the magnitude K. Thus, the magnitude of B is equals to Ka, that is mode of Ka, where K is constant, A is magnitude of vector A. So, we can say that if K is positive, vector B has same direction as of vector A. And if K is negative, vector B has the opposite direction as of vector A. The next thing we are going to study today is subtraction of vectors. Let there be two vectors, vector A and vector B. So, subtraction of two vectors can be done as vector A plus negative of vector B. Let's get to see in the figure. Let there be two vectors A and B. As I told, this is vector A, this is vector B, and negative of vector B would be in the opposite direction. So, this is vector minus B. Let angle between the vector A and vector minus B be phi. So, the resultant force would be vector A plus negative of vector B. We can see here as well. The resultant force would be A square plus B square plus 2AB cos phi to the power 1 by 2. Or we can say that under root of A square plus B square plus 2AB cos phi, where phi is the angle between the vector A and vector B, or negative of vector B. So, what we have learned in today's session? The first thing we have learned is basic introduction to physics. What was the basic introduction? Physics is the study of laws of nature, and mathematics is the language of physics. What are units and what are measurements? What we have learned in units and measurements? Units are basically of two types, fundamental or base units or derived units, where fundamental units have the properties of invariability and availability, and derived units are being derived from fundamental units only. The next thing we have learned is deriving dimensional formulae. We have learned the dimensional formula of velocity is Lt minus 1. Further, we have studied differentiating between scalar and vector quantities. What are scalar quantities? Scalar quantities are the one which has magnitude only, like mass, temperature, and the scalar quantities can be added with general algebraic rules of maths. What are vector quantities? Vector quantities are the one which have both magnitude and direction, and the vector quantities have been added by triangle rule of vector addition, or it is also called as parallelogram law of vector addition. We have also studied multiplication of vectors and subtraction of vectors, where addition of vectors meant to be by the formula a square plus b square plus 2ab cos phi to the power 1 by 2, or under root of a square plus b square plus 2ab cos phi. This was the parallelogram law of vector addition. Today, on the course of Physics Basics, we are standing on week 2. Here today, we are going to study about motion force, momentum, and torque. Before going ahead, let's get into the recap. In the last session, we have covered Introduction to Physics, units and measurements, scalar and vector quantities. What's on the plate today? On today, the table of contents as follows. Motion, frame of reference, motion with constant acceleration, inertia, Newton's law of motion, force, types of forces, momentum, torque. The learning objectives of today's session will cover the concept of motion and rest, application of Newton's law of motion, application of different types of forces on a body, basic definition of momentum and torque, and how they are calculated and can be understood. Let's get started with motion. What is rest and what is motion? When a body is said to be at rest, let's get to know it with examples. When the position of the body does not change with time, it is called to be at rest. Examples: an apple lying on a table. It's not changing its position with the time. Suppose at time t equal to 0, it is at rest, and at time t equal to 5 seconds, it would be at the same position. Apple would not change its position by itself. So, the apple is lying on a table and said to be at rest. The second example could be a flower pot on the ground. Similarly, as of apple, flower pot couldn't change its position by itself with the time. Thus, the flower pot is said to be at rest. When is a body is said to be at motion? When the position of the body changes with time, it is said to be in motion. It could be understood with the examples. A person playing cricket. Here, we can see that as the ball comes closer to the batsman reacts accordingly for the shot. Thus, its body is said to be in motion. Another example from which we can study the body at motion is a moving truck. We can see here the truck is moving in forward direction. Thus, it is said to be in motion. Note: the term motion depends on the body under consideration and the viewer. Like suppose here, the driver is in the rest relative to the truck as he is sitting inside the truck. Or we can also say that the truck and its driver are both in motion relative to the road. I mean to say that if a person is standing on the road, he would say that both driver and the truck is moving in forward direction. Or the driver himself is the observer, then he would say the truck is moving, I am at rest. The next thing we are going to study is frame of reference. Frame of reference is required for locating the position of any object or particle. Example: with respect to the road, the car moves and cycle does not. It means the observer is standing on the road and talking about a frame of reference called road, where the car is moving on the road and cycle is still. This infers that road is the frame of reference. Frame of reference. The next thing we are going to study on frame of reference is motion in a straight line. Consider an object traveling at a distance x at a time t. Then velocity of the object would be written as v is equals to dx by dt. Let's get to know this example with the help of figure. This is an object at time t is equals to 0. It is at rest. Thus, the distance is equals to 0. At time t, the object travels a distance x. Therefore, the velocity of the object can be written as dx by dt. If dx by dt is positive, the direction will be in the positive x-axis. Here is the coordinate axis given. Similarly, if dx by dt is negative, the direction will be in negative x-axis. Further, we can also find out about the acceleration, as acceleration is given by the formula dv by dt, that is change in velocity with respect to time. If dv by dt is positive, the acceleration will be in positive x-axis as given in the coordinate axis, positive x-axis. Similarly, if dv by dt is negative, the acceleration will be in negative x-axis. The next thing we are going to learn is motion with constant acceleration. Motion with constant acceleration. Consider an object. Let the object be a ball that has been traveling in a straight line with constant acceleration. Thus, since the ball is at rest at time t is equals to 0, let's consider its velocity u. As the ball moves in a straight line with constant acceleration, it would move to a different point with a velocity v. The time taken to reach the velocity v from u, it would be t. Thus, at time t is equals to 0, velocity was u. At time t is equals to t, velocity is v. Here, we have to assume that the acceleration is constant. Thus, as the acceleration along the straight line is constant, acceleration can be written as dv by dt, where acceleration is actually is change of velocity with respect to time. As we have seen earlier that initial velocity of the ball or of the object was u, and the final velocity of the object or ball was v. Similarly, the time has also been changed there. The initially, since the ball was at time is equals to 0, to attain the velocity from u to v, the time taken was t. Therefore, acceleration here is written as dv by dt. Further, by applying the cross product rule, dv is equals to a dt. Since the initial velocity was u and the final velocity was v, thus we have to integrate dv by from u to v, and ADT would also be integrated in the manner such that the initial time would be taken as 0 and the final time to achieve the velocity v would be t. Thus, dv would be integrated from u to v is equals to ADT to be integrated from 0 to t. Applying integration rules, this can be written as v from u to v is equals to a. As a constant, it would be out of the brackets, and t would be written as big bracket t from 0 to the time t, where 0 is the initial time, t is the final time. required to attain the velocity v from u. Thus, v minus u is equals to at minus 0, where a is acceleration and is constant. Applying integration rules here, t could be written t when integrated from 0 to t can be written as t minus 0. Thus, v minus u, the LHS would be same as the last. V minus u is equals to at minus a0, which is actually 0. So RHS would be directly written to only at. Thus, the equation written here is v minus u is equals to at. This can also be written as v is equals to u plus at. Let's consider this as equation 1. Getting further, we need to first understand the difference between distance and displacement. Let's consider an object, that is a ball, that does two movements simultaneously. The first movement would be from here to this point. The second movement would be from this point to return back to this point. All the motions would be done on a straight path, but in different directions. The movement 1 would be in positive direction. The movement 2 would be in negative direction. As we can see, at movement 1, the ball moves from x is equals to 0 to x is equals to 5 meter. Thus, the distance travel at movement 1 is 5 meters. At second step, ball moves to point this. That is, movement 2 is from time t dash to t. So, the distance travel in movement 2 is just 2 meters, since the position of the ball here is 3 meters only. So, the ball was at rest. So, at time t is equals to 0, x is equals to 0. Then ball moved to point this, where at time t dash, the distance x is equals to 5 meter. Further, the ball returned back to some point, and where the time required to go back is at time equals to t, the distance travel was 3 meters. Thus, the net distance traveled by the ball is 5 meters plus 3 meters is equals to 8 meters. But if we talk about the displacement is the shortest distance travel. Thus, the shortest distance travel from point 1 to the final point is just 2 meters, since 3 meters has been traveled from here to here. The 2 meter has been traveled from here to here. Thus, the displacement would be just 2 meters. The distance would be 8 meters. 5 plus 3, 8. After knowing the difference between distance and displacement, let's get further. Here, x is actually displacement, not distance. It was important to understand the difference between distance and displacement for these formulas. As we have learned earlier in equation 1, v is equals to u plus at, and v was the final velocity, where we also know that the formula of velocity is distance upon time, or displacement upon time, that is dx by dt. Change in distance with respect to time is called velocity. Thus, v can be written as dx by dt is equals to u plus at. Multiplying u plus at by dt, we can write it as dx is equals to u plus at dt. As we know that the distance traveled was from point 0 to x, thus dx would be integrated from lower limit 0 to upper limit x, and the RHS of the equation u plus at dt would be integrated from 0 to t, because at time t is equals to 0, the body was at rest and at point 0. But as the ball moves forward, at time t is equals to 0, the distance traveled by the ball is x. Applying integration rules, we can write as x is x in the big bracket with limits 0 to x is equals to u dt and at dt. This has been written after the multiplication of u with dt and at with dt, where a is acceleration, t is time, u is the initial velocity, and dt is change of time. Thus, applying integration on each of the RHS points, u dt can be written as u dt integration from lower limit 0 to upper limit t, plus integration of at dt would be similar from lower limit 0 to upper limit t. Thus, applying integration rules here in this equation, we can summarize this equation as x is equals to ut plus half at square, where the x, u, t, a have their usual meanings as x is displacement, u is initial velocity of the object, t is the time required to achieve the velocity v, or to time required to get into the position x, plus half at square was a is acceleration of the body and t is the time required to achieve the velocity v or to reach at the point x. This whole equation is written as equation 2. Further, for getting ahead, we already know that equation 1 was v is equals to u plus at. After squaring the equation 1, we would get v square is equals to u plus at square. The LHS of v square would be v square only, but we can see here a mathematical formula applying. Mathematical formula we have studied in basic classes is a plus b's whole square, the whole square of a plus b, and that is actually a square plus b square plus 2ab. So we are going to apply the same mathematical formula here, where a is equals to u and b is equals to at. Therefore, the RHS can be written as u square plus a square t square plus 2u at. Thus the complete equation could be read as v square is equals to u square plus 2u at plus a square t square. The LHS could be written as same, where RHS can be also written as u square plus 2a, where we have taken the common 2a from the above equation. Thus, u square plus 2a to be multiplied by ut plus half at square. Can we see something similar that we have studied in the previous slide? Ut plus half at square. Yes, this was equation 2. And ut was half at square was equals to x. Therefore, putting equation 2 here, we could simplify this complete equation by writing it as v square is equals to u square plus 2ax, or v square minus u square is equals to 2ax. This we can write it as equation 3. Thus, as a result, we can see that for solving a problem of straight line motion with a constant acceleration, the following equations can be of use. The equations are equation 1, v is equals to u plus at. Equation 2, x is equals to ut plus half at square. The third equation is v square minus u square is equals to 2ax, where all the symbols have their usual meanings, like v is equals to final velocity of the object, u is equals to initial velocity of the object, a is equals to acceleration attained by the object, t is equals to time required to reach at the point x or time required to reach at the velocity v. And what is x? X is actually the displacement. As we have learned earlier, the difference between distance and displacement. Displacement is the shortest distance traveled. To the second session. What we have learned in the first session was the motion within constant acceleration of an object. There, we get to know about the three equations that are really useful in solving numericals. The first equation was v is equals to u plus at. The second equation was x is equals to ut plus half at square. The third equation was v square minus u square is equals to 2ax. Using these equations, we are going to solve a few examples to know the application of these equations and to better understand them in practical life. This is example number 1. Suppose a person goes on a morning walk in a semicircular park of radius r is equals to 50 meter. If he walks from point A of the park to the point B, find the distance covered by the person and the displacement of the person. As we can see that this is a semicircular park, thus the distance covered by the person would be is equals to circumference of semicircle. The formula for circumference of semicircle is equals to pi r, where pi is equals to 3.14 and is a constant in the formula, and r is the radius of semicircle, that is 50 meters. On product of pi r, that is 3.14 into 50, we get that 157 meters. This is the circumference of semicircle, and so the distance covered by the person while going from point A to point B would be 157 meters. The second thing that needs to be found out is displacement. What is displacement? Displacement is the shortest distance between the A and B. So, as we can see in the park, from point A to point B, there is only a one possible shortest distance, that is this straight line. Thus, the displacement done by the person from going from point A to point B is diameter of the park. and diameter of the park can be written as 2 times radius of the park, right? Where r is radius, which is equals to 50 meter. Thus, putting values on this formula, we get that 2 into 50 is equals to 100 meters. Thus, the final answers of the questions are: the distance traveled by the person for moving from point A to point B is equals to 157 meter. Also, we can say that the displacement covered by the person from point A to point B is 100 meters. Let's get into the second example. The question is, an object starts from rest with constant acceleration. Okay, so this is the object and this is moving with a constant acceleration. Let's see how. At time t, velocity is u, that is 150 meter per second. So we got to know that initial velocity of the object was 150 meter per second. At time t plus 1, the velocity is v, equals to 250 meter per second. That is the final velocity of the object achieved at time is equals to t plus 1 is 250 meter per second. We need to find acceleration and the distance traveled during the t plus 1th second. Okay, so how we are going to find it? What is acceleration? Acceleration is change in velocity with respect to time and is denoted by the letter a. Change in velocity is final velocity, that is 250 meter per second, minus initial velocity, that is 150 meter per second. The change in velocity is 250 minus 150. With change in time is only 1 second, because t plus 1 minus t, that would be only 1. Thus, acceleration can be written as 250 minus 150 divided by 1, which would be equals to 100 meter per second square. This is the answer of the acceleration, the first part of the question, that is 100 meter per second square. The second part of the question was distance covered during the t plus 1th second, that is denoted by x, distance. Okay, so applying the third equation here, which was v square minus u square is equals to 2ax. Here v square is 250, actually 250 square of 250, since v was the final velocity. The square of v square is square of 250. U was the initial velocity, which was 150 per meter per second. So square of u is square of 150. So LHS can be written as v square minus u square can be written as 250 square minus 150 square. The RHS was is equals to 2ax. A is acceleration, x is the distance. Thus, we have already found out A is 100 meter per second square. That is our answer of the first part of the question. And x, we need to find it out. Therefore, 2 into 100 meter per second square into x. Thereby, by solving the equation, we get that x would be equals to 200 meters. Further, let's get into the example 3. Example 3. So, question tells us about a ball. A ball of 5 kg mass was at rest before sliding on a 3.6 meter frictionless plane. The acceleration of the ball is observed as 5 meter per second square. We need to determine the change in velocity of the ball. So, the given things are initial velocity of the ball is 0 meter per second and is denoted by u, as it is already written as ball was at rest. Final velocity is denoted by v. Therefore, the change in velocity is equals to final velocity minus initial velocity. But since we have seen that the initial velocity was 0 meter per second, therefore change in velocity would only be equals to final velocity, that is v. Okay. So by applying the third equation of motion, that is v square minus u square is equals to 2ax, where they have their usual meanings. V stands for final velocity, u stands for initial velocity, a stands for acceleration attained by the object, x is the distance. Thus, in our equation, we are going to put numerical values. So v would be written as v only, v square, u is 0, so square of u is square of 0, 2 is a constant, so 2 that has to be multiplied by a, which is 5 meter per second square as given in the question. X is 3.6 meter, since the plane that on which the ball has been traveling is of 3.6 meter frictionless plane. Thus, by solving this equation, we find out that v square is equals to 36, and by under root of the v square we get the value of v, that is the final velocity, which is 6 meter per second. Thus, as we need to know the change in velocity of the ball, therefore initial velocity was 0, final velocity is 6 meter per second. So change in velocity would be is equals to final velocity, which is 6 meter per second. So this is our answer to the question. The next thing we are going to study here today is inertia. What is inertia? Inertia is a particle's state of rest or uniform motion along the straight line. We can try to understand this by using example. Okay. The first example, that is the tendency of a coin to stay at rest. The example 1 details as the coin placed on the card will tend to be at rest when card is stroked, as coin will get into the glass. Let's try to understand this. Suppose there is a glass filled up with water and a card is placed on the glass to cover it. Also, a coin is placed on the glass. Thus, as we stroke the card from a direction such that the card moves away from the glass, we will tend to see that the coin still goes inside the glass instead of moving with the card. This happens because of tendency of a coin to stay at rest. As we see that the coin was at rest before also, but as the card starts moving, the coin tries to stay at rest only. It doesn't try to move with the card. Although it was resting on the card, but it was not trying to move with the card. It was trying to be at rest, and thereby it falls inside the water. The second example through which we can understand inertia is the football. Let's say the football tends to be in the motion while meeting the net when kicked. So let's say that a football player was kicking the ball into the nets. Thus, as the player kicks the ball tends to be in motion as long as it can be. Like, it takes nets with the ball to a different position unless it stops. Thus, there comes a point in the nets where ball and nets move together just because the ball tends to be in motion and doesn't stop on facing the net. We could also understand this by the following example. Let m1 and m2 be the mass of two particles. respectively, and a1 and a2 be their acceleration. Referring to figures, we can see here that this is the particle 1 having mass m1 and acceleration a1. Similarly, this is particle 2 having mass m2 and acceleration a2. Suppose an equal force is applied on both, then the acceleration of particles will never be same. Thereby, a1 will never be equal to a2. This is because a1 would never be equal to a2. Thus, this could be understood by if m1 is greater than m2, that is mass of first particle is greater than the mass of second particle, then acceleration of the first particle would be less than acceleration of the second particle. If the mass of first particle is greater than the mass of second particle, then the acceleration of the first particle would be less than acceleration of the second particle. Through this, we can understand that larger will be the inertia on acceleration 1, that is on particle 1. In the second case, we can make out that if the mass of first particle is less than the mass of second particle, then the acceleration of the first particle would be greater than the acceleration of the second particle. That is, smaller will be the inertia of particle 1 as compared to particle 2. Thus, it can be concluded that inertia is directly proportional to the mass of the body. That is, inertia is directly proportional to the mass of the body, as I have written this as in mathematical way also. We can also refer to the figures. If the mass of the body is larger, the inertia would be larger. If the mass of the body is lesser, the inertia would be lesser. We can also refer the previous slide, where the mass of the ball was greater than the nets. Therefore, the ball tends to be in motion and take nets with it. Otherwise, if the mass of the nets would be greater than the mass of the ball, then nets would have stopped the ball then and there, because the nets would tend to be at rest, and that would have made the ball to be at rest as well. The next thing we are going to study today is Newton's law of motion. The Newton's law of motion. Newton has given 3 laws. The first is Newton's first law of motion. What Newton's first law of motion tells us that a body in a state of rest or in a state of motion remains to be as such until and unless subjected to an external force. This can also be said as if the summation of all the forces acting on an object is 0, then the particles remains unaccelerated. This is called Newton's first law of motion. Let's try to understand this using an example. An object of mass 0.30 kg is suspended from a string, as given in the figure. An object A of mass 0.30 kg is suspended from a string. Then force acting on the object is equals to mass into acceleration due to gravity, where mass is denoted by m and acceleration due to gravity is denoted by g. Let's consider the g, that is acceleration due to gravity, is equals to 9.8 meter per second square. Therefore, by providing the values to this equation, we can write mass as 0.30 kg to the product of 9.8, that is acceleration due to gravity, equals 2.94 Newton. If object is at rest, then following shall be the condition, like pull from earth will be equal to pull from string, right? Pull from earth would be equal to pull from string. Therefore, the tension of the string would be also be equal to 2.94 Newton. Next, we are going to study Newton's second law of motion. The Newton's second law of motion states that the time rate change of the momentum of a body is equal in both magnitude and direction of the force applied on it. Mathematically, force is equals to mass into acceleration, or force can also be derived as a rate of change of momentum, where momentum is product of mass and velocity. Let's try to understand this through the derivation of momentum. Let m be the mass of the box. Here, this is the box of mass m, moving with a velocity u, and at time t is equals to 0, its velocity is u. When a force is applied from horizontal direction, then the box will attain a velocity of v at time t. Therefore, the initial momentum of the box would be mu, that is mass of the object into initial velocity of the object. Similarly, final momentum of the box would be is equals to mv, that is mass of the object into final velocity of the object. Therefore, change in momentum is equals to mv minus mu, and rate of change of momentum can be written as mv minus mu divided by time, that is t. Taking m is common from the above equation, we can write v minus u divided by t. We already know that change in velocity per unit time is written as acceleration and denoted as a. Therefore, the second law of motion can be derived to a point where F, that is force, is equals to mass into acceleration. The next thing that we are going to study is working with Newton's first and second laws of motion. For understanding the working of both the laws, let's consider an example. Consider a box of mass m pulled by a string by an angle phi on a table. So this is the mass of the box m, and it is being pulled by an angle phi. Let frame of reference be the box. Thus, force acting on the box R, pull of the string T, this is the pull of the string T, that would be acting along the string, that is along the string. The second force that would be acting is the Earth's gravitation force is mg, and that would act in vertically downward direction, in the direction of Earth. The third force that would be acting is the table's contact force. The contact force of table is, suppose, E, that would act vertically upward. So this is the free body diagram denoting all three forces with their directions. Tension force with an angle phi, Earth's gravitational force with the direction downwards with the box, downwards to the box, and contact force of table, that is E, which would act vertically upwards. To make the free diagram, we should consider three steps. That is, step 1, decide the system frame of reference. Okay, so first we need to decide on which frame we are going to find out the force acting on him. Step 2, identify the forces action on the object. So we need to identify like pull of the string, Earth's gravitational force, and the table's contact force. Step 3. Make the free body diagram. So we made a free body diagram showcasing all the forces with their directions. Thus, along the x-axis, we need to find out the number of forces acting. So the tension force would have add the component T cos phi. How T cos phi has come here? Since it was acting with angle phi on the box and the force was T. So on an x-axis, it would make a component of T cos phi. Component of mg would be 0 since mg is acting completely in vertical direction, vertically downward direction actually. Similarly, component of force E would also be 0 because since it is acting in vertically upward direction, therefore its component on x-axis would be 0. Therefore, total force along the x-axis would be T cos phi plus 0 plus 0, that concludes to only T cos phi that has been acting along the x-axis. Using Newton's law, we can write that T cos phi is equals to ma. Therefore, T is equals to ma upon cos phi. Let's give this equation a name as equation 1. Thus, we need to also find out forces acting along the y-axis as well. Component of T, that would be T sin phi. How this has come? The box has been pulled by a string with the force T, making an angle phi with the table. So, T sin phi would be here or here. Component of the force of gravitation, that was mg. So that would be minus mg. And the component of E would be E, since it is working directly on vertically upward direction. Hence, the total force along the y-axis is equals to T sin phi plus negative of mg, that is minus mg, plus E. Also, we can put the value of T from equation 1 in this above equation. So, this equation can be written as E is equals to mg minus ma tan phi. Newton's third law of motion. So Newton's third law of motion states that every action has an equal and opposite reaction. Or, if a force F is exerted by a body on the body B, then at the same time body B will exert a minus F force on body A. The best example to understand Newton's third law of motion is rocket propulsion. As we can see in this figure that a rocket is going to propel straight. So there are a few forces acting on it. The first force that we consider here is force on gases. As the rocket is emitting the force of gases, thus it would allow hot gases to come out from itself, and the reaction of this force would be force on the rocket. Thereby, the rocket will move up. We try to understand this again. As the action happens, the reaction will surely happen. As the gases would come out with force from the rocket will move up. The same thing is written here. The emission of gases from rocket acts as an action for the reaction on rocket by forcing it to fly in the air. So let's get into the exercise. The question says a body of mass 5 kg is suspended by strings. That is, a body of mass 5 kg is suspended by strings. And the body makes an angle 45 degree each with the horizontal. The body makes an angle with the strings of 45 degree from the horizontal axis. Here we can see that on the string 2, 45 degrees angle made by the body and the horizontal axis. Similarly, 45 degrees angle being maintained by string 1 and the horizontal axis. Find the string tensions. Let T1 be the tension of the string 1 and T2 be the tension of the string 2. Therefore, and we should also consider force due to gravity, acceleration due to gravity as 9.8 meter per second square. Entering into the solutions, force acting on the body are force of gravity, that is acting downwards, T1, that is force by the string 1, that is tension of the string 1, that would act along the string, T2, that is tension of the string 2, that would also act along the string, along the second string. T1 is along the first string, T2 is for along the second string. Thus, taking horizontal components, we can write as T1 cos 45 is equals to T2 cos 45. How we can write that? Since this is making an angle 45 degree with in between string 2 and the horizontal axis. If we consider this as a right angle triangle and apply trigonometry rules, thus in the horizontal axis we can write it as T2 cos 45. In the similar fashion, here string 1 is making a 45 degree angle with the horizontal axis. If we consider this as right angle triangle and apply basic trigonometry rules, we can write the force acting on the horizontal axis is T1 cos 45. Therefore, while taking the horizontal components, T1 cos 45 is equals to T2 cos 45, or cancelling out cos 45 from LHS as well as RHS, we can write as T1 is equals to T2. Let's name this equation as equation 1. Further, taking vertical components in the free body diagram, we can write T1 sin 45 plus T2 sin 45 minus mg is equals to 0. Let's find out why it is written like that. Again, consider this. The string 2 is making 45 degree angle with the horizontal axis. If we consider a right angle triangle here, then we can assume that by applying trigonometry rules, this side would be is equals to T2 sin 45 degree. Similarly, this side would be is equals to T1 sin 45 degree. As string 1 is making 45 degree angle with the horizontal axis and we are considering this as a right angle triangle. Also, we are in the vertical direction, there is acting force due to gravity. This force due to gravity is mg and it is acting in the downward direction. Therefore, a negative sign would be add up with this. Therefore, taking total vertical components, we can write it as T1 sine 45 degree plus T2 sine 45 degree minus mg is equals to 0. From equation 1, which was showcasing us T1 is equals to T2, we put that in here. Thus, this equation of vertical components T1 sine 45 degree plus T2 sine 45 degree minus mg is equals to 0 can be written as T1 sine 45 degree plus T1 sine 45 degree minus mg is equals to 0. Since T1 is equals to T2, we have already seen in equation 1 here in previous slide. Therefore, by putting values to these equations, we consider that sine 45 is 0.707 and acceleration due to gravity is 9.81 as provided in question. Thus, T1 into T1 sine 45 would be T1 into 0.707 plus T1 sine 45 again, that would be T1 into 0.707 minus mg. Minus mg would be m is 5 kg. So minus m into 9.81 is equals to 0. Further, taking common from these equation, we can write it as twice of T1 into 0.707 minus 49.05 is equals to 0. How we are able to write this? Twice of T1 into 0.707, as this is the first time we are getting this T1 into 0.707 in this equation. This is the second time we are seeing this T1 into 0.707 in this equation. So therefore, we are able to write it as twice of T1 into 0.707. And how we got 49.05? 9.81 when multiplied by 5 gives the results 49.05. Therefore, equation is twice of T1 into 0.707 minus 49.05 is equals to 0. Thus, T1 is equals to 34.65 newtons. Thus, we can find it out as the tension applied on the string 1 is equals to 34.65 newtons. As from the equation 1, we have seen that T1 is equals to T2. So, string 2 would also be facing a tension of 34.65 Newton. Let's get into the another exercise. The question says, if a cable supporting an elevator has a tension of 1.5 kilonewton, calculate the elevator's weight. While considering acceleration due to gravity is equals to 9.8 meter per second square. Let's see this in free body diagram. So this is an elevator of mass m. Let's say its mass is m and it has been supported by a cable of tension T1 where T1 is equals to 1.5 kilonewton as given in the question. We have to consider that acceleration due to gravity is 9.8 meter per second square. So if we consider this as system, there are two forces acting on this system. The first one is T1. The second one is force due to gravity. That would be is equals to m into g. G is 9.8 meter per second square and m is the mass of the elevator that we have to actually find out. So considering mass of elevator V m and we are taking vertical components since there are no horizontal components in this. Therefore, tension of the cable T1 would be equal to weight of the elevator, that is m into g, where they have usual meanings. T1 is the tension on the string 1. There is only one string attached. tension on the string 1, m is mass of the elevator, and g is acceleration due to gravity. Putting values to these equations, we can write as 1500 is equals to m into 9.8. Thus, m, that is mass of elevator, is found out to be 153.06 kgs. The next thing we are going to study is force. What is force? What is its units? So, force represents the push or pull on an object and alters its velocity. This can also be written as force is equals to mass into acceleration. Since it alters the velocity, so there will always be an acceleration. The picture depicts the same. A body of mass m moving with an acceleration a. It is due to the force that would cause a force. Force would be equals to mass into acceleration. Thus, its derived unit is kg meter per second square. Kg is the unit of mass, meter per second square is the unit of acceleration. So the unit of force will be kg meter per second square. This can also be written as Newton. Thus, kg meter per second square and Newton have same meaning. As the force has both magnitude and direction, therefore, force is a vector quantity. Another way to describe force is as an external agent that alters a body's state of rest or motion. Likewise, here a body was at rest and the force on the application of force, it starts to move. The similar thing can happen if a body is moving and a braking force is applied to deaccelerate the body and to make it at rest. The next thing we are going to study is types of forces. Force can be categorized into 4 types: gravitational force, electromagnetic force, nuclear force, and weak force. Where gravitational force and electromagnetic force comes under the category of classical physics, and nuclear force and weak force comes under the category of quantum physics. We have already seen this table before on the day 1 course, where I have classified this as when the particle size is termed to be greater than 10⁻⁻⁶ meter and the particle is moving with less than the velocity of 10⁸ meter per second, then it comes under the category of classified physics. Therefore, in classical physics, gravitational force and electromagnetic force will work on it. In the similar manner, if the particle size is less than 10⁻⁻⁶ meter and the particle is moving with a velocity of 10⁸ meter per second, then quantum physics would be applied on it. Application of quantum physics means the nuclear force and weak forces will be applied on it. Let's study in detail what is gravitational force. Newton's law of universal gravitation is usually stated as every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Also, Earth's gravitational force is called gravity. Let's try to understand this definition again. Every particle attracts every other particle in the universe. The first half of the statement is every particle attracts every other particle in the universe with a force, and that particular force is directly proportional to the masses of both particles, and that particular force is inversely proportional to the square of the distance between their centers. Let's try to understand this gravitational force using an example. Let m1 be the mass of the first body, m2 be the mass of the second body, and r be the distance between the two bodies. Here in the picture we can see that m1, this is the first body, and the mass of the first body is m1. This is the second body, and we have considered the mass of the second body as m2. And as per the gravitational force, both the bodies will be applying force on each other. And the distance between the center to center distance between the bodies is considered to be r. Therefore, from the definition, we can make out that the force acting is directly proportional to mass of the two bodies, m1 and m2. Also, the force acting is inversely proportional to the square of the distance between them. The square of the distance between them here is r. Therefore, combining both equations, force can be written as equals to G into m1 into m2 divided by r square, where G is the proportionality constant and can be called as universal gravitational constant as well. And the value of G is equals to 6.67 into 10 power minus 11 Newton meter square per kg square. Gravitational force by Earth on small bodies. That's the next thing we are going to study. Consider mass of Earth as me is equals to 6 into 10 power 24 kg, and the mass of the object be m2 kg, and the radius of the Earth is equals to 6400 kilometer, where these are actual facts. Mass of the Earth is 6 into 10 power 24 kg. Radius of Earth is 6400 kilometer. Since the object is placed on the Earth's surface, the distance between the Earth and the object is equal to the radius of the Earth. Hope you have got this. The object of mass m2 is placed on the surface of the Earth. So, the center to center distance between the object and the Earth would be is equals to radius of the Earth, that is 6400 kilometer. Hence, the gravitational force can be written as F is equals to G me into m2 upon r square. Here me is mass of Earth and G is gravitational universal constant. m2 is mass of object. Thus, this equation can be written as 6.67 into 10 power minus 11, which is the value of universal gravitational constant, into 6 into 10 power 24, which is the value of mass of Earth, into m2, that is the mass of the object, divided by 6400 kilometers square, which is square of radius of the Earth. This can be simplified as taking constants at one end and m2 at the other. So constants into m2. Further, these all constants can be covered by a single word called g. This is acceleration due to gravity. If we calculate these constants, we would get a number called 9.81. Here, g is acceleration due to gravity and would equal to 9.81 meter per second square. And g is considered to be same for objects placed on Earth. Thus, to simplify the calculations, we have considered a constant named as small g, which is called acceleration due to gravity. Thus, the formula for calculating the gravitational force by Earth on small bodies placed on it changes to F is equals to g into m2. m2 is mass of the small body that has been placed on the Earth. Let's try to understand this using an example. Here, as the question given, calculate the gravitational force acting between the Earth and the Sun. Considering mass of the Sun is equals to 1.99 into 10 power 30 kg. Mass of the Earth is equals to 6 into 10 power 24 kg. And distance between the Sun and the Earth is equals to 1.49 into 10 power 11 meters. So we have got mass of Sun as ms. We denote it by ms. So mass of Sun is 1.99 into 10 power 30 kg. Mass of Earth, that is m2, or here in our case is me, is 6 into 10 power 24 kg. Center to center distance, that is r, between Sun and Earth is given as 1.49 into 10 power 11 meter. So, as per the formula of gravitational force between two bodies, F is equals to G into ms into me divided by r square. Ms can be termed as m1, that is mass of first body, that is mass of Sun. Me can be termed as mass of Earth or mass of second body. Thus, putting values to this equation, we can write it as universal constant value is 6.67 into 10 power minus 11 multiplied by 1.99 into 10 power 30, which is the mass of the Sun. Further, this is multiplied by 6 into 10 power 24, which is mass of the Earth. And this whole is divided by r square, that is center to center distance between the Sun and the Earth, which is 1.49 into 10 power 11 meter whole square. On summarizing this equation or solving this equation, we get that in the numerator is equal to 79.64 into 10 power 43 to be divided by 2.22 into 10 power 22. And thus, the force acting between the Sun and the Earth is equals to 3.587 into 10 power 22 newtons. Thus, gravitational force acting between two bodies, Sun and Earth, is 3.587 into 10 power 22 Newton. This is also the answer of this question. Here, we close our session 3. Session 4. In this session, we are going to study about electromagnetic force. If two resting particles are having charge of Q1 and Q2 respectively, and both are at rest with respect to the observer. Also, if they have distance r between them, then the electromagnetic force can be defined as by the formula 1 upon 4 pi E naught into Q1 into Q2 divided by r square. Let's try to understand this. Suppose there are two charged particles, Q1 and Q2. Charge on first particle is Q1, charge on second particle is Q2. They are r distance apart, and this has been observed via observer. Then the electromagnetic force acting on both the particles is 1 upon 4 pi E naught into Q1 into Q2 divided by r square. Here E naught is equals to 8.85419 into 10 power minus 12 Coulomb square divided by Newton meter square. This E naught is also called vacuum permittivity constant. Thus, by putting value of E naught on this equation, we can write this bracket as 1 upon 4 pi E naught is equals to 9 into 10 power 9 Newton meter square per Coulomb square. This is to be noted that when the charge Q1 and charge Q2 have different charges, then the type of force will be different accordingly. Let's suppose the charge on Q1 is positive. The charge on Q2 is positive. Therefore, the force will be repulsive. Case 2. If charge on Q1 is positive, charge on Q2 is negative, force will be attractive. Case 3. If charge on Q1 is negative and charge on Q2 is positive, force will be attractive. Case 4. If charge on Q1 is negative, if charge on Q2 is negative, then force will be repulsive. So conclusively, we can say that if charge on both the particles are same, then the force will be repulsive. If charge on both the particles are different, then the force will be attractive. Like here, charge on both particles is positive. Also here, charge in both particles are negative, then the force is repulsive. Similarly here, if the charge on one particle is positive and the other particle is negative, then the force will be attractive. Let's see the example where there are two hydrogen atoms and are 1 meter apart. So we have to find out that the number of forces acting on each particle. Here in the diagram it is depicted that there are two hydrogen atoms, atom 1, atom 2. Both the atoms contain a proton and a neutron. This is proton and neutron of atom 1. This is proton and neutron of atom 2. Thus, solving the problem, here we can see that the number of particles in one atom is 1 proton plus 1 neutron. Number of particles in one atom is 1 proton, 1 neutron. Thus, total number of particles is 2. Total number of atoms is 2. This is atom 1. This is atom 2. So, total number of particles in the system is 4. This is 2 plus 2. 2 plus 2. Total number of particles 4. Force acting on each particle is equals to 3. Let's see how 3 forces are acting on each particle. Let's consider force acting on the neutron of atom 1. It has been showcased by the orange color. So we have to find out wherever the orange arrows are moving, or from how many directions this neutron of orange color is getting forces. So the first thing we can see is it is getting force from yellow arrow. This yellow color is of neutron of second atom. Similarly, it is also receiving a force of blue color from this blue particle, which is proton of second atom. Also, this is receiving a force in form of red arrow, that is from the red particle, and that is from the proton of its own atom. So, neutron of the atom 1 is getting 3 forces. So those forces are from proton of its own atom, proton of the second atom, and neutron of the second atom. So neutron of the first atom is getting 3 forces. On the similar pattern, we can find out that neutron of the second atom is getting three forces. That is, one from the neutron of the first atom, second force is from the proton of the first atom, and third force is from the proton of its own atom itself. In the similar fashion, we can see that the proton of the second atom is also facing three forces. The first force is from proton of the first atom, the second force is from the neutron of the first atom, and the third force is from the neutron of its own atom. And vice versa for the proton of first atom. Therefore, total number of forces acting on complete system is, here its system is said to be of containing two hydrogen atoms. Force acting on each particle is 3 and total number of particles are 4. So total number of forces would be equal to 4 into 3 is equals to 12. The next thing we are going to study here today is nuclear forces. Nuclear forces act only on proton and neutron of an atom. These forces are highly attractive and have a very short range. When separation between the particle is greater than 10 to the power 14 meter, then Coulomb's force is stronger than nuclear force. On the other hand, if the separation between the particle is 10 to the power minus 15 meter or less, then nuclear force is stronger than Coulomb's force. This nature of having attraction at 10 to the power minus 15 meter causes the nucleus to be stable. Thus, nuclear forces allows a nucleus to be stable. The example of such forces are nuclear fission and nuclear fusion. The next forces that we are going to study is weak force. Have you heard the term negative beta decay? Let me tell you. A neutron has the ability to transform into proton while also emitting an antineutrino and an electron. The term for this is negative beta decay. The force responsible for these are known as weak forces. Weak forces are also have smaller range than the size of neutron and proton. Therefore, these weak forces also come under the category of quantum physics. Thus, its effect can only be seen in the neutron and proton only. The next thing we are going to study is momentum. What is momentum? Momentum is a vector quantity and it represents the mass that is in motion. Here, it can be calculated as product of mass and velocity. As we can see, this is an object of mass m moving with a velocity v. Therefore, momentum of the object can be written as p is equals to mv, where p is denoted for momentum, m is mass of object, v is velocity attained by the object. Since the unit of mass is kg and the unit of velocity is meter per second, therefore the derived unit for momentum is kg meter per second or Newton second. In a uniform motion where the velocity is constant, momentum will also be constant. Let's try to understand this. Suppose if a body of mass is moving with a velocity v, the mass of the body is never going to change by itself. So mass will definitely be m at every point of time. And we have considered that the velocity is constant, and velocity, that means the velocity is also not changing. So if both mass and velocity are not changing, that is that if the both are constant, then momentum will always be constant. The next thing we are going to study is torque. What is torque and what is its unit? Torque can be described as the twist or angular force provided to an object around an specific axis. In other words, it is the product of magnitude of force and perpendicular distance from axis of rotation. Let's try to understand these in the form of pictures. Here, a horizontal bar has been given a torque. Here, the torque can also be said as the rotational force. Therefore, it has been written as F, the rotational force. Rotational force is also called torque. So, when a rotational force is provided on a horizontal bar through an axis of rotation, the horizontal bar will revolve. This is called torque. Force is also a vector quantity and torque is the rotational force. So, in these things, generally the objects will try to rotate or revolve. In force, the object can move in a linear direction as well. In the same picture can be visualized like this also. This is the side view of the picture and this is the top view of the picture. When a force is applied on a horizontal bar, the bar will try to rotate along an axis. That axis is called the axis of rotation. This is the axis. This is the direction of rotation. This is application of force on a horizontal bar. At time is equals to 0, when force equals to 0, the horizontal bar was at rest. But at time is equals to t, the horizontal bar would be somewhere here due to the application of rotational force on the axis of rotation. Consider an object of length r on which F force is applied from its one end. Therefore, the torque can be defined as force into distance from the axis of rotation. Here in this case, it is the length of the horizontal bar. Torque here is represented by the letter capital T. Also, it has been generally mentioned with the Greek letter tau. Tau is equals to force into the displacement. Displacement is distance from the axis of rotation. Force, application of force from the distance of axis of rotation. Thus, its derived unit is Newton meter and it is a vector quantity. Let's try to understand this torque by an exercise. The question says, an internal hexagonal bolt is to be opened using a wrench of length 0.3 meter. The force applied by hand through wrench is 3 newtons. Find the torque on the bolt. So, given the length of the wrench is somewhere 0.3 meters. 0.3 meters. The force applied through the wrench is 3 newtons. The force applied is 3 newtons. Therefore, torque applied by wrench is force into the length of the wrench. The formula of torque is magnitude of force into distance of the point from the axis of rotation, which is 0.3. In our case, 0.3 meters. So, 3 into 0.3 will lead to 0.9 Newton. So, for opening a bolt or loosening a bolt, a 0.9 Newton of force is to be needed. And so is the answer of our question. Here we summarize the today's session. In this session, we have covered the following things. The first thing that we have covered is Newton's first law. Newton's first law states that A body at rest or in motion remains to be at rest or in motion until and unless an external force is applied on it. This is due to inertia. That is, a body, when it is at rest, it would be at rest only if no external force is applied on it. Similarly, if a body, if it is in motion, it will be in motion only until and unless an external force is applied on it. For example, suppose a vehicle is moving with a constant velocity of 10 meter per second. Until and unless the braking force is applied, it would not stop. On a similar fashion, if a vehicle is standing still on the road, until and unless the engine force allows its tire to move, it would not start to move. So it would tend to be at rest if at rest, and if it is in motion, it would be in motion until and unless an external force is applied. The second key point we have learned today is Newton's second law of motion. Newton's second law of motion states that rate of change of momentum of a body is equal in both magnitude and direction of the force applied on it. By deriving the second law, we have found out that force is equal to product of mass and acceleration, where mass is mass of object and acceleration is the acceleration achieved by the object. Thus, we figure out that the acceleration of a particle can be measured as the sum of forces acting on it divided by its mass. We have simplified that equation for acceleration. Previously, we have termed it as force is equals to mass into acceleration, F is equals to ma. Now for finding particularly acceleration, we have simplified that is A is equals to F upon m. Further, we have learned Newton's third law of motion. The Newton's third law of motion states that every action has an equal and opposite reaction. The example we've preferred for this is the rocket propulsion. The amount of gases, the force by which the gases are emitted by the rocket decides how fly the rocket will go up in the sky. This was the example we used for the Newton's third law of motion. That is, every action has equal and opposite reaction. Action was the force of the gases and the reaction was the flying of the rocket on the sky. We have also studied here today the four types of forces. Those are gravitational force, electromagnetic force, nuclear force, and weak force. We have also concluded that gravitational force and electromagnetic force comes under the category of classical physics, whereas nuclear force and weak force comes under the category of quantum physics. And this has been classified based on the particle size and the moving velocity of the particles. We have also studied momentum, where momentum can be defined as the product of mass and velocity of the body. Further, in the last, we have studied torque, which is not the least. Torque is the rotational force acting on the body and can be calculated as the force applied multiplied by the perpendicular distance from the axis of rotation. That is, torque represented by del T or generally been represented by tau is equals to force applied, that is F, into perpendicular distance from the axis of rotation, that is R. So torque is equals to F into R. Here we close our today's session and today's classes. Hope you have learned very much about force, momentum, torque, etc. Thank you. Hello everyone. Today we are standing on week 3 of the Physics Basics course. And today on session 1 we are going to start very soon. On week 3 course we are going to study about work, power and energy. Also we are going to cover conservation of energy and momentum. First, let's get into what we have learned before in the week 2 session. In the last session, we have covered motion, frame of reference, motion with constant acceleration, inertia, Newton's law of motion, force, types of forces, momentum, and torque. These are the table of contents of today. It contains basics of work, power, and energy, work energy theorem, power, conservation of mechanical energy, principle of conservation of momentum. The learning objectives of the week 3 course would be as following. We are going to understand what is work, effect of direction of force on calculation of work, types of mechanical energy, conservation of mechanical energy, and conservation of momentum. So, let's begin with work, power, and energy. What is energy? In very simple words, it could be explained as the capacity to do work is called energy. Since the energy is defined via work, thus its unit is same. It's joule and denoted by capital J. Let us try to understand energy using an example. A standing man is less energetic as compared to a running man. As you can see in the pictorial representation that when a man is standing, just he looks very less energetic as compared to a running man. Also to mention here, standing is also a verb, running is also a work. Both standing and running is work. So the energy has been utilized in both the ways. While standing, a man utilizes energy, and while running, also man utilizes energy. But when we have to say who is more energetic, then surely a running man would be more energetic than a standing man. Energy of an object is in motion is given as Ke is equals to half mv square, where Ke is kinetic energy. And let's get to know what is m and v. M is the mass of the body. In our case, the mass of the person. In this case, the mass of the person who is standing. In this case, mass of the person who is running. Similarly, v is velocity of the person. Like in this case, velocity of a person with which he is running. So, m is mass of our body and v is velocity of body. So, kinetic energy can be represented as Ke is equals to half mv square. Further, Ke, that is kinetic energy of a system of objects, is the sum of kinetic energy of its constituents. Suppose there are multiple objects in a system. Thus, the total kinetic energy of the system would be is equals to summation of half mv square, where I is the number of objects in the system. Now, let us get to know what is kinetic energy in a straight line motion. Kinetic energy represents the energy possessed by an object due to its motion. So, if an object is in motion, it would definitely have some kinetic energy. The variation in kinetic energy is directly proportional to the speed. So, as we have already known in the previous slide that kinetic energy is equals to half mv square. So, this means that kinetic energy is directly related to the mass of the body and speed of the body. So does this statement denotes that kinetic energy is directly proportional to the change in speed. Let us assume two objects, object A and object B. Suppose an object A is being coming downwards towards the earth. So it would be a free falling object coming from the sky. The force acting on object A would be equals to gravitational force of earth. Similarly, object B is thrown upwards. Since the object B is moving towards the sky due to the force exerted by a person, thus two forces would be acting on object B. The first force would be the upward force by which object B is thrown. The second force would be the gravitational force of the earth. Both the forces, the upward force by which the object is thrown in the sky and the gravitational force that has been acted by the earth, would be in opposite direction. This system of two objects shows us that when object A was falling, then also kinetic energy was there in object, and when object B was going towards the sky, then also kinetic energy was there in the object B. So we can depict that kinetic energy, there is presence of kinetic energy in a straight line motion. This slides tells us the same thing. When a ball A falls towards the Earth's surface, the force of gravity will be in direction of its velocity. Hence, kinetic energy will increase. Let's see this in the figure again. When a ball A falls towards the Earth's surface, the force of gravity would be in the direction of velocity. As the ball is falling downwards, so the velocity would be acting in downward direction of A, and gravitational force would definitely act in the downward direction. So both velocity and gravitational force will be in same direction, thereby causing change in kinetic energy, and that change would cause an increase in kinetic energy. Similarly, when ball B is projected upwards, the gravitational force will oppose its velocity. Hence, the kinetic energy will decrease. Let's see this in figure. This is ball B, and when ball B is thrown upwards, then there will be an upward force acting on the ball, making it to move towards the sky, whereas the gravitational force will cause to pull the ball downwards. Therefore, both upward force and gravitational force would be in opposite direction. Also, since the ball is moving upwards, thus the direction of velocity would be upwards. Rather, we see that the direction of gravitational force is downwards. Therefore, both velocity and gravitational force will be in opposite direction, and this will cause kinetic energy to decrease. Now, let's study kinetic energy in a circular motion. That in an object, if the resultant force is acting perpendicular to its velocity, then the object's speed will not change. Thus, kinetic energy does not change. Let's try to understand this using the following table. Let the direction of resultant force be tangential to its velocity. Then the kinetic energy would change. The second case would be when the direction of resultant force is perpendicular to its velocity. Then kinetic energy will not change. Let's try to understand this using an example. Suppose an object is attached to a string and rotated at a high speed. An object, this ball, is attached with a string and it is rotated at a high speed. Then the tension and the velocity of the object are always perpendicular. Since the object is moving in the rotational motion or circular motion, thereby this string would act as the radius of the circle, and the object velocity would always be tangential to the circle. Thereby, this is the direction of the velocity of the ball, and this is the radius of the circular motion in which ball is traveling. Therefore, the tension does no work done in circular motion. Thus, as seen in picture, that this tension will cause zero work done on the ball, since this string tension and direction of velocity is tangential to each other, thereby work done is zero in circular motion. Next, we are going to study its derivation. From definition of kinetic energy, we can make out that kinetic energy is equals to half mv square, where kinetic energy with change of time can be written as dk by dt is equals to d by dt of half mv square. We are keeping time as an aspect to this equation. Thereby, Ke is written as dk by dt. That is kinetic energy with respect to time. Similarly, on the right hand side, with respect to time, the change in kinetic energy would be d by dt of half mv square, where K is kinetic energy, m is mass of body, and v is velocity of body. Thereby, reshuffling it, we are getting m dv by dt into v. Here, this has been done to write off, this has been done to get force here as an important factor of kinetic energy. Like we always know that force is equals to mass into acceleration. We can see mass here, mass of the body, and we already know acceleration denoted by a can be written as dv by dt. Since the force is tangential, thus it can be written as ft, and this complete thing can be grouped together to write ft, where ft is m dv by dt. ft is equals to m dv by dt, and v comes as it was here, thus it is here. So kinetic energy can be written as ftv, where ft is the resultant tangential force. How it is calculated? The resultant tangential force is calculated as mass of the body into change of velocity per unit time, that is acceleration. Further, dk by dt can be written as ft into dr by dt. Here in this equation we have elaborated the v. V is velocity of the body, that can be written as dr by dt, where r is the distance traveled, and we already know that velocity is equals to distance traveled per unit time. Thus we have managed to elaborate v and have written this equation as dk by dt is equals to ft into dr by dt. Cancelling out time from this equation, we get that dk is equals to ft into dr. dk represents the work done, ft is resultant tangential force, dr is the distance covered by the object. Thus, dk is equals to ft into dr. One thing to be noted here is when the angle between the resulting force and the velocity is phi, then the resultant force becomes ft is equals to f cos phi. Let me explain that. When the resultant force and velocity makes an angle phi, then the resultant force becomes ft is equals to f cos phi. We have already studied that when the resultant force makes an angle 90 degree with the velocity, that is when the resultant force is perpendicular to the velocity, then the ft becomes f cos 90, which is equals to 0, since cos 90 is equals to 0. Thus, resultant tangential force would be 0. Now, in the next slide, we are going to study about the types of work done that we usually see. That is, when would be the work done would be positive, when would be the case where the work done would be 0, and when would be the case where the work done will be negative. This we are going to study in this slide. So, let there be 3 conditions for this. Let's get into the condition 1. Here, let's suppose the angle made by the force acting and the velocity is phi. Then we can see that if the angle is less than 90 degree, then the work done would be greater than 0. That is, the work done would be positive. Let's try to figure out that why the work done would be positive. As we already know that work done is ft cos phi, as we have studied earlier. Therefore, value of cos phi would be positive whenever the angle phi is less than 90 degree. we already know that cos 90 is 0. Thus, when value of phi is less than 90, then cos phi is always positive. Therefore, work done would be always positive. Coming to the condition 2, here we see that the force and the velocity both are acting perpendicular to each other. Therefore, the angle phi made between them is of 90 degree. As we have studied earlier that work done is equals to Ft cos phi, and moreover we already know from basic mathematics and trigonometry that cos phi when phi is equals to 90 degree is equals to 0. Thus, when the tangential force is multiplied by 0, it would give the result as 0, and thus the work done in this condition would always be 0. Coming to condition 3. Here, in this case, the angle phi made between the force and the velocity is greater than 90 degree. Thus, when, as we already know, that work done is Ft cos phi, and since the angle made between the force and velocity is greater than 90 degree, so from basic trigonometry, we get to know that when the value of cos 90 is 0 and when the value of phi is greater than 90, then cos phi is negative. Therefore, when negative value is multiplied by Ft, that is tangential force, then the net work done would be negative. Let me reiterate this complete situation. In condition 1, when angle phi was less than 90 degree, the work done would be positive. In condition 2, when angle phi was equals to 90 degree, the work done would be 0. In condition 3, when angle phi is greater than 90 degree, then work done would be negative. Now let's get to know what is work energy theorem. Work energy theorem. Let dk is equals to Ft into dr, and this dk is equals to Ft into dr can be also written as k2 minus k1 is equals to Ft into dr. How this came from? Let us refer to the previous slides. Here in the last equation we have seen that dk is equals to Ft into dr, where dk represents the work done, Ft is the tangential force acting on the body, and dr is the distance traveled by the body. Thus, coming back to our slides, we see that we can write dk as k2 minus k1, that is difference in kinetic energy. K2 minus K1. K2 be the final kinetic energy, K1 be the initial kinetic energy. Then K2 minus K1 is equals to Ft into dr. Hence, the resultant force does work on an object that is equal to its kinetic energy change. This line depicts the same. The change in kinetic energy directly be equal to resultant force of the work. Let F1, F2, F3 and there be n number of forces acting on the object. All forces are separated to each other, and when the object is subjected to these n number of forces, then the work done by the resultant force on the object is work done is equals to F1 plus F2 plus F3 plus dash 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 up to the Fn into dr, where Fn is the force exerted on the object by the nth term. The unit of work is Newton meter or joule, where joule can be represented by the capital J. Next, we are going to study how can work be calculated. For understanding that how work can be calculated, we have to refer this figure. Here, a mass of block is attached with the spring, and there are three cases of the spring. In case 1, the spring is at its natural length. In case 2, the spring is compressed by an amount x. And in case 3, the spring is elongated by an amount x. The same things are mentioned here. A spring can be positioned in three different ways. the spring in its natural length, that is case 1, the spring when it is compressed by an amount x, and the case 3, spring elongated by an amount x, that is our case 3. So we would be calculating the net work done by the spring on the system. Let us assume that the initial state of the spring is natural and the final state of the spring is compressed. And if x1 is the position of the initial state of the spring and x2 be the state of final stage of the spring, thus in this case when the spring was at natural state in its initial state, then x1 would be 0, and when the spring is at final state then and it is compressed, then x2 will be minus of x. Therefore work done by the spring would be minus of 1 by 2 kx square. Coming to the next condition, let us assume that the initial state of the spring is natural, that is case 1. Then the final state of the spring is elongated, case 3. Then the distance traveled by the spring would be x. The distance traveled would be x. Therefore x1 would be is equals to 0, x2 is equals to x. Thereby work done would be half kx square. In another case, we can see that if the initial state of the spring is elongated, case 3, and the final state of the spring is natural, case 1, therefore the position of the spring at initial and final stage would be x1 would be is equals to x initially and x2 would be is equals to 0 finally. Therefore the net work done would be is equals to half kx square. In the similar manner, if the initial state of the spring is compressed and if the final state of the spring is natural, that is we are talking about the initial state compressed, that is case 2, and the final state, that is case 1, natural length of spring. There we can see that at initial position of the object would be minus x and final stage would be 0. Then the net work done on the object would be half kx square. Coming to last two conditions, let the initial state of the spring be elongated, case 3, and let the final state of the spring be compressed, case 2. Thereby we would see that the initial point, the position of x1 would be x, the position of x2 would be minus x at final stage. Thus the net work would be done is equals to 0. The last condition states that when the initial state of the spring be compressed and the final state of the spring be elongated, that is we are talking about case 2 and case 3 again, where case 2 is our initial state of spring and case 3 is our final state of spring. Thereby the values of x1 would be minus x and the value of x2 would be plus x. Thereby the net work done by the spring would be 0. If we try to make this table more easy to understand, then we can see that the net work done at the final state of the spring minus the work done at the initial state of the spring. Here the work done at the final state would be minus half kx square minus 0. Therefore net work done is minus half kx square, where k is spring constant, x is the distance covered by the spring. Here on this note, we are going to close our session 1. Thank you. Now let's get started with session 2. We already have studied how to calculate work in case of spring. Now in session 2 we are going to see this using an exercise. Here in question 1 it is given that a spring having an 80 Newton per meter spring constant is compressed by 3 cm from its native position identify the work the spring force has done. Thus, the given conditions are: there was a spring with a spring constant 80 Newton per meter, and we denote this spring constant as K. Further, the given conditions of the question are: the displacement observed by the spring is X, which is equals to 3 centimeter. Here, since we are using SI unit standard, thus 3 centimeter shall be needed to convert it into meter, where 100 centimeters is equals to 1 meter. Therefore, 3 centimeter would equal to 0.03 meter. We have used the conversion factor. 100 centimeter is equals to 1 meter. Therefore, 3 centimeter is equals to 0.03 meter. Thus, the magnitude of work done would be half kx square. This we have already studied in previous slides, that the formula for work done is equals to half kx square, where k is the spring constant of the spring and x is the displacement observed by the spring. Putting values to this equation, we can write this equation as half into 80 into 0.03 square. Since in the formula there was square of x, thereby we need to do square of 0.03 meters. After calculating this equation, we get the result as 0.036 joules. Thus, this is the answer of the question, where the spring of 80 Newton meter spring constant was compressed by 3 centimeters. Then, the work applied on the spring is 0.036 joules. Now, let's get into the another exercise. Let there be two objects A and B. This is object A, this is object B. Let's suppose object B exerts a force FBA on A. So, object B is exerting a force on A, B on A, FBA. Thus, this will cause object A to move towards object B, and thereby the kinetic energy of A would increase. Let's see this again. When the object B would exert a force on object A, then object A will tend to move towards object B, and this would increase the kinetic energy of the object, as the object would move with some velocity, causing an increase in kinetic energy. Let's get ahead. Also, when object A exerts a force FAB on B. So, getting back to this figure, object A will also exert some force on object B. That force would be named as FAB. That is force exerted by object A on object B. FAB exerted by A on B. This will cause object B to move towards object A, and since the object B would start moving, it would gain some velocity, and this would cause change in kinetic energy. Thereby, the kinetic energy of B would increase. Concluding these conditions, we can figure out that FBA plus FAB would be is equals to increase in total kinetic energy of two objects. That is, the kinetic energy of the system, where the system consists of two objects, object A and object B, would be increased definitely. But how that we calculated is that FBA plus FAB would be equal to total change in kinetic energy, or total increase in kinetic energy that would be caused by two objects. Also, we need to know that FBA is equals to minus of FAB. Hence, the FBA plus FAB is equals to 0. Here, we just shifted this FAB on the LHS side to write this equation as FBA plus FAB is equals to 0. This is because both the forces remain opposite to each other direction wise. As we have seen in the figure, FBA was acting on this direction from right to left, that is from B to A, whereas the FAB force was acting on this direction, that is from left to right, that is exerted by A on B. Therefore, the direction of FAB and FBA were opposite, and hence proves that FBA plus FAB is equals to 0. Since the force acting on the both objects are opposite, therefore, since the direction of force on both objects are opposite, therefore the displacement are also opposite. The change in kinetic energy of system is equal to work done on system by both external and internal forces. Also, we got to know that work done on different system of objects by the internal forces may not be zero. Thus, concludingly, we can say that work is caused by both external and internal forces. That was stated in point 1, where point 2 states that the net work done by the internal forces may not be zero. Next, we are going to study about power. What is power? The rate of doing work is power. Mathematically, it can be expressed as P is equals to dW by dt, where P is denoting power. dW is the net work done in the time t, that is work done per unit time. Therefore, power is work done per unit time. Also, work can be written as FDR, as we have studied earlier that work is equals to force into displacement. Here, F is the force, dr is the displacement. Thus, putting this equation in the equation of power, we can write the equation of power as P is equals to FDR. dW can be replaced by FDR divided by dt, where dr and dt are grouped together to be called as dr by dt, and F is taken out as separate from the brackets. Somewhere we also know that dr by dt is equals to v, where v is velocity of the object. Therefore, this equation of power can be written as P is equals to F into V, where F stands still as the previous equation and dr by dt is being replaced by V. Therefore, the formula of power is equals to P is equals to F into V. Its derived unit is joule per second or watt. So, the unit of power is joule per second, generally said as watt. Also, watt is denoted by the letter capital W. Also, it is to be noted that another unit of power is horsepower. It is represented by capital H and capital P, that is HP. H from the horse, P from the power. So, HP, where 1 HP is equals to 746 watts. Now, in this slide, we are going to understand about power using a numerical. Here, the question states that an 800 kg elevator must be lifted at a 0.20 meter per second constant velocity. Thus, calculate the minimum horsepower of the motor that needs to be employed. Consider acceleration due to gravity, that is small g, is equals to 9.8 meter per second square. So, the question states us that there is an elevator of mass 800 kg and we need to lift that elevator with a velocity of 0.20 meter per second. Considering the acceleration due to gravity, that is g, is equals to 9.8 meter per second square, and we have to calculate the minimum horsepower of the motor that is required. Coming to the solutions. Here, minimum power required for lifting elevator can be found out by using the formula of power, which is denoted by capital P, where we have already studied the formula of power is equals to P is equals to F into V, where F is the force applied and V is the velocity. We already know that force applied can be written as multiplication of mass and acceleration due to gravity, where mass is denoted by m and acceleration due to gravity is denoted by g. Putting the values in this equation, we get that mass is equals to 800 kg, that is the mass of elevator, and acceleration due to gravity is to be considered as 9.8 meter per second square. Thereby, the net force applied on the elevator would be 800 into 9.8 meter per second square, that would result in 7,840 newtons. Therefore, minimum power required for lifting elevator would be F into V, force into velocity. We have already calculated the force as 7,840 Newton and the velocity is given in the question, that is 0.2 meter per second. Therefore, the minimum power required is multiplication of 7,840 force into 0.2 meter per second of velocity. That would result in 1568 watts. Since the power required by the motor should be given in the HP as requested in the question, thus we have to convert this unit into horsepower. Thus, minimum power required for lifting elevator in horsepower, that is HP, is equals to, we have already learned before the relation between horsepower and watts, where 1 horsepower is equals to 746 watts. Using this relation, we would find out how much horsepower will be there for 1568 watts. Thus, by cross multiplying in this equation, we get 1 into 1568 divided by 746. That would result an answer of 2.1 horsepower. Therefore, the minimum power required for lifting elevator is 2.1 horsepower. Next, we are going to study about potential energy, that is the second part of mechanical energy. There are two types of mechanical energy, kinetic energy and potential energy. Till here, we have already studied about kinetic energy. Now, we are going to study about potential energy. What is potential energy? Any object or system that has stored energy as a result of its position or component arrangement is said to have potential energy. Generally, the potential energy is being denoted by capital U. It can be described as three characteristics that a specific has: the shape of an object, the position of an object, readiness to transform into kinetic energy. Thus, this point states that if an object has some kind of shape or position, or it has a readiness to transform itself into a kinetic energy, then surely there is some potential energy in that object. Mathematically, gravitational potential energy can be written as mass into acceleration due to gravity into height of the object. Here we can see the use of these three characteristics. The position of an object. This characteristic has been used to find out the gravitational potential energy. Position of an object, here it is mentioned height of the object. How high or how low the object is placed. Depending on that, an object will possess some kind of potential energy, where gravitational potential energy can be written as mass into acceleration due to gravity into height of the object, where mass is denoted by m, acceleration due to gravity is denoted by g, height of the object is denoted by h. Therefore, m into g into h. Similarly, elastic potential energy can be written as half into spring constant k into square of spring divided by elastic displacement x square. This equation has been derived from the Hooke's law, where k represents the spring constant and the square of spring per unit elastic displacement is being represented by x square. Therefore, elastic potential energy can be written as half into spring constant K into square of spring upon elastic displacement, that is half kx square. Further understanding this using a numerical. The question states that find the potential energy of body of mass 5 kg kept at a height of 2.5 meter. Consider acceleration due to gravity, that is small g, is equals to 9.8 meter per second square. Thus, as given in the question, the mass of the body is equals to 5 kg. We denote mass as small m. Height at which it has been kept is 2.5 meters, that is from the grounds. So, the height of the object is given, that is h has been given, and we have to consider acceleration due to gravity, that is small g, is equals to 9.8 meter per second square. Using the formula of potential energy, we already know that capital U is equals to mgh, m into g into h, where U is the potential energy, m is the mass of the body, g is acceleration due to gravity, and h is the height at which the object is positioned. Thus, putting the values to this equation, we need to place 5 kg on m, that is mass of the body, 9.8 as acceleration due to gravity, and 2.5 the position of the object from the ground. Thereby, on calculating this equation, we get potential energy is equals to 122.5 joules. Next, we are going to study about conservation of mechanical energy. Till here, we already know that mechanical energy has been categorized into two. First one is kinetic energy. The second one is potential energy. Now, we are going to study about conservation of mechanical energy. For understanding the conservation of mechanical energy, we need to consider this example. So, here, let's consider a block and spring are connected. Thus, when the block is pulled and released, the block will move towards the center A, where the velocity would be v0. Understanding this with the figure, we can see that a block is attached with the spring, or a block is connected with a spring. There can be three cases. Here, on the first case, when the block is pulled from its natural point A. A is the point where spring is at its natural length. Thus, the block is pulled from point A and then released. This would cause the block to move towards A with a velocity of v0. Further, the block again move towards the center but with the different velocity v1. Let's try to understand this using figure. This was the condition 1, when the block is pulled from its resting point A and it has been pulled to this point, and further it has been released. This would cause the block to move in left direction with the velocity of v0. The velocity v0 will tend the block to pass through point A, that was its resting point. This would cause the spring to compress and block will pass through point A. Further, after compression, when spring wants to get back to its natural length, then the direction of block would be opposite again, and this time the block would be moving with a velocity of v1 and might be again passing through point A. Thus, comparing case B and case C, the block and the spring has the same configuration. Here, when block was at its natural length, when the spring at its natural length, and the case C where spring was compressed. In both the systems, they were having almost same configuration. At position A, the spring has the same length, but due to the friction, the kinetic energy of case B is greater than kinetic energy of case C. Further, based on the above trial or exercise, we can write as force are divided into two categories. Category 1, that is conservative forces. Category 2, that is non-conservative forces. During a cycle, if the force does no work, it is considered to be conservative force. On the other hand, if not, it is called as non-conservative force. Let me try to explain this again. If the force causes no work to be done, then the force is conservative. And if the force causes some work to be done in a cycle, then the force would be non-conservative. Example of conservative forces are as follows. Examples are force of gravity, Coulomb's force, spring force. That means these all forces does no work during a cycle. Therefore, these are called as conservative forces. On the other hand, the example of non-conservative force is equals to force of friction. That means force of friction does some work during the cycle. Therefore, it is called as non-conservative force. Further, we need to understand that potential energy is described based on the conservative internal forces, as we can write it as UF minus UI is equals to minus of W is equals to minus of KF minus KI. That means UF is the final potential energy, UI is the internal potential energy, W is the work done, KF is the final kinetic energy, Ki is the initial kinetic energy. Thus, this equation states that UF minus UI is equals to minus of work done is equals to minus of Kf minus Ki. Let's denote this equation as equation 1. Thus, equation 1 represents as total mechanical energy is the combination of potential and kinetic energy. Also, whenever internal forces are conservative in nature and external forces do not work, the total mechanical energy of the system remains constant. Let's try to understand this. If suppose the internal forces are conservative in nature, that means, as we have already studied in point 1, potential energy is described based on conservative internal forces. And it is suggesting then when the internal forces are conservative, that it does no work, then the total mechanical energy of the system would be constant. Also, it has been mentioned that total mechanical energy is the combination of potential and kinetic energy. This is known as the principle of conservation of energy. When non-conservative forces act on the system, example frictional force acting on the system, the total mechanical energy K plus U does not remain constant. That is, whenever the non-conservative forces start acting on the system, then there would be some change in kinetic and potential energy, and thereby the total mechanical energy would not remain constant. But the work energy theorem would still hold there. What is work energy theorem? We have studied that before. So let us refer that again. The work energy theorem states that the resultant force does work on an object that is equal to its kinetic energy change. This is work energy theorem. Thus, whenever the non-conservative forces act on the system, the total mechanical energy, kinetic energy plus potential energy does not remain constant, but work energy theorem would still apply there. Here, on this note, we end our session 2. Thank you. So, let's start with session 3. We have already studied about conservation of mechanical energy. We have started conservation of mechanical energy in session 2. Now, in this session, let's continue the conservation of mechanical energy. Let there be WC be the work done by the conservative internal forces on the system. Let WNC be the work done by the non-conservative forces, internal forces on the system. Let WEXT be the work done by the external forces on the system. Let me remind you that WC is conservative internal forces. WNC is non-conservative internal forces. C is for conservative internal forces. NC is for non-conservative internal forces. So WC is work done by conservative internal forces and WNC is work done by non-conservative internal forces. And WEXT is equals to work done by the external forces on the system. WEXT, we have assumed three things: WC, WNC and WEXT. Then, in accordance with the work energy theorem, all forces work is equal to the kinetic energy change. Therefore, using this statement, we can write that work done by the conservative internal forces plus work done by non-conservative internal forces plus work done by external forces on the system. Thus, sum of these all work done would be equal to Kf minus Ki. That is kinetic energy final minus kinetic energy initial, where we already know that work done by conservative forces can be written as minus of UF minus UI. How we know that? Let me refer to previous slides. Here, in the point 1, we have already mentioned potential energy, that is U, is described based on the conservative internal forces. The same thing is here. Conservative internal forces. WC is work done by conservative internal forces. Therefore, work done by conservative internal forces can be written as minus of UF minus UI, where UF stands for final potential energy and UI stands for initial potential energy. Thereby, we can write this equation as work done by non-conservative internal forces plus work done by external forces is equals to Kf plus Uf minus Ki plus Ui. How we have simplified this equation? The LHS of WNC and WEXT stands there, whereas WC, that is work done by conservative internal forces, has been replaced by UF minus UI, and thereby we have shifted WC on the right hand side to write it as Kf plus UF minus Ki plus Ui, where Kf is final kinetic energy, UF is final potential energy minus initial kinetic energy Ki plus initial potential energy, that is Ui. Considering this Kf plus Uf as the final energy of the mechanical system, we can write this as Ef. Also, considering Ki and Ui as the total mechanical energy at the initial stage of the system, we can write this as Ei. So, Ef is equals to Kf plus Uf, Ei is equals to Ki plus Ui. Therefore, the net energy would be equals to Ef minus Ei is equals to WNC plus WEXT. Further, we can study that if external forces do the work and internal forces are conservative, the work done by the non-conservative forces is equals to 0. This statement concludes to 2 points. The first thing, if the external forces do the work and internal forces are conservative, then work done by non-conservative forces is equals to 0. So work done by non-conservative forces would be 0. The second thing it would communicate is the WEXT then is equals to EF minus EI. That is, work done by external forces would be is equals to EF minus EI. Energy at the final stage of the system minus energy at the initial state of the system. Next, we are going to study about the conservation of momentum. The conservation of momentum. So let's find out what is momentum. Linear momentum of an object is given by momentum is equals to mass into velocity, where momentum is denoted by capital P, mass is denoted by small m, and velocity is denoted by small v. Thus, P is equals to m into v, where P is momentum, m is mass, and v is velocity. In case there are n objects, the total momentum would be the sum of momentum of all the individual objects. That is, in this case, the total momentum can be mathematically written as Pn, where n stands for n number of objects. So Pn would be equals to summation of Mn into Vn, where Mn would stand for mass of n number of objects and Vn would stand for velocity of n number of objects. Therefore, this equation can be written as Pn is equals to summation of Mn into Vn. It is to be noted that an object moving with a constant velocity will have uniform linear momentum unless and until an external force acts on it. This states that if an object is moving with a constant velocity, since I have already told you in the previous sessions that P is equals momentum is mass into velocity. We have already studied today as well. So P is equals to mass into velocity. Mass is never going to change itself. So if the velocity is constant, the momentum will also be constant. And thereby, until and unless an external force is acted on it, momentum will remain constant. According to Newton's third law of motion, every action has equal and opposite reaction. We have studied this law previously, that every action has equal and opposite reaction. We have also considered the example of rocket propulsion. Thus, we can also consider a different example in this case. For example, during a leap, the force applied by your legs is equal to opposite to the force applied by the ground. Like, if a person is moving on the ground, if he is walking, then the force applied by his legs on the ground will always be equal and opposite to the force applied by the ground on his legs. This states the Newton's third law of motion. To understand the conservation of momentum, let us consider a case. Let u1 and u2 be the initial velocities of mass m1 and m2, and v1 and v2 be their final velocities respectively. Thus, change in momentum of object A would be equal to m1 into v1 minus u1, since the momentum is written by mass into velocity. Here v1 is the final velocity of the object 1, whereas u1 is the initial velocity of object 1. So change in velocity would be v1 minus u1, and mass of object 1 is, that is object A, is m1. Thus, net change in momentum of object A can be written as m1 into v1 minus u1. Similarly, change in momentum of object B can be written as m2 into v2 minus u2. The same theory will apply here. m2 is the mass of object B, v2 is the final velocity of object B, u2 is the initial velocity of object B. Therefore, change in velocity would be v2 minus u2. Therefore, change in momentum would be m2 into v2 minus u2. As per the Newton's third law of motion, it can be written as FBA is equals to minus of FAB. That is, mathematically, Newton's third law is written as the force applied by the object B on object A is equals to negative of force applied by object A on object B, where FBA can be written as m2 into a2. We have read this previously also. Force is equals to mass into acceleration, and since here FBA is the force that has been applied by object B, therefore formula can be written as m2 into a2. Also, we know that a2 is the acceleration of the object B, and acceleration is defined as change in velocity per unit time. Therefore, acceleration can be more elaborately written as v2 minus u2 divided by time. That is final velocity of object B minus initial velocity of object B with respect to time. Therefore, FBA can be written as m2 into v2 minus u2 divided by time. Let's state this equation as equation 2, and FBA is equals to minus of FAB. Let's state this equation as equation 1. Here A2 is acceleration of m2. That is, as I told earlier, A2 means acceleration of object B and mass of object B is m2. We have discussed this earlier. In the similar manner, FAB can be written as m1 into A1, where m1 is the mass of object A and A1 is the acceleration of object A. FAB is force exerted by object A on object B. We have also discussed previously, acceleration is change in velocity per unit time. Therefore, for object A, the change in velocity, that is A1, that is thus for object A, acceleration can be written as change in velocity, that is v1 minus u1 divided by t. Let's state this equation as equation 3. Here also we have discussed a1 is the acceleration of object A with mass m1. Coming to the next slide, we are putting equation 2 and equation 3 in equation 1. So let's revise what was equation 2 and equation 3 first. Equation 2 was force exerted by object B on object A is equals to m2 into v2 minus u2 divided by time. That is m2 into u2 v2 minus u2 divided by time. Similarly, equation 3 was FAB, force exerted by object A onto object B, is equals to m1 into v1 minus u1 divided by time. Thus, by putting equation 2 and equation 3 in equation 1, the equation 1 is FBA is equals to negative of FAB. We can write as m2 into v2 minus u2 divided by time is equals to minus of m1 into v1 minus u1 divided by time. Hope you have understood. This is FBA. This is FAB. And negative of FAB to be true. Therefore, by simplifying this equation, we can get the following results. m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. This is the mathematical equation for conservation of momentum. Here, m1 and u1 plus m2 u2 is the total momentum of objects A and B before collision. Since u denotes the position at the initial point, therefore, this is for the objects A and B before colliding. This is the state of momentum of the objects A and B before colliding. Similarly, m1 v1 plus m2 v2 is the total momentum of object A and B after collision. As we know, v is the final state of final velocity of the objects A and B. Therefore, m1 v1 and m2 v2 denote total momentum of object A and B after collision. Thus, from this last point, we need to understand that what is collision and how it happens. Collision. For understanding collision, let us try to understand the following example. Consider two blocks of mass m1 and m2. This is mass first block of mass m1. This is second block of mass m2. Both the blocks are moving with a velocity of v1 and v2 respectively. This first block is moving with a velocity of v1. This second block is moving with a velocity of v2. It is also shown that the second block is attached with a spring. Thus, few conditions. Case 1, where time is t1. This pictorial representation of collision represents that both the blocks are moving in the same direction. First block is of mass m1 is moving with a velocity v1, whereas second object of mass m2 is moving with a velocity of v2. Here, the comparison of velocities is also given. That is, the velocity of object 1 is greater than the velocity of object 2. This has been very clearly mentioned here. In the second case, when time is t1 plus del t1, that is, due to the higher velocity of object 1, this object at time t1 plus del t1 collides with the second object. Thus, such will be the representation of the system, that the object 1 is colliding with the object 2. This would cause the spring to compress and transfer of velocity. Thus, thereby we can see here v1 is lesser than v2, whereas in previous case v1 was greater than v2. That is, velocity of first object was greater than velocity of second object. That only tend this object to get collide with second object. And when the collision happened, the velocity of first object get reduced and thereby it is now smaller than the velocity of the second object. This arrow denotes the same. The velocity of second object is greater now with the velocity of first object. This is our case 2. Further, going to case 3, at time t1 plus del t1 plus del t2, what would happen is that spring will exert a force back to the object 1. Like we have seen in the case 2, that the spring was exerting a force, but that force was kx in the positive direction and minus kx in the negative direction. So this minus kx force would exert a force such that the velocity v1 would get decreased, and this plus kx would exert a force on second object, that this velocity v2 would increase. This must have happened in case 2. But what happened in case 3? When the velocity of first object decreased, then the mass has been detached from the spring, and now the second object is moving with a pace of velocity 2, and the velocity 1, which is much lower than the velocity 2, causes the first object to get it detached from the spring and stay apart from the object 2. Here, the same things are mentioned. u1 and u2 be the initial velocities of mass m1 and m2. Let v1 and v2 be the final velocities. Considering potential elastic energy of spring is half kx square. Thus, due to the absence of external force, the momentum of two blocks of the system stays constant throughout the process, since, as we see, that there was no external force applied by anyone or any other object, thereby the momentum of the blocks in the system stays constant, and due to the lack of friction, the sum of elastic potential energy and kinetic energy remains constant. These are the points which we have seen in this pictorial view very clearly. Further, we can say that total energy of the system at time t1, the spring is at its natural length, is half m1 u1 square plus half m2 u2 square is equals to E. Let's give this equation name as equation 1. Further, total energy of the system at time t1 plus del t1, that is case 2. At case 2, the total energy of the system would be half m1 plus m2 v square plus half kx square is equals to E. In such a state, the spring would be at its compression state, and the compression, we would believe that the compression is maximum. Also, we would say let u1 is equals to u2 is equals to v. Thereby, we have replaced u1 and u2 with the v. Thus, we can write that half m1 plus m2 v square plus half kx square is equals to E, where half kx square is the force exerted by the spring. Going into the case 3, total energy of system at time is equals to t1 plus del t1 plus del t2. The compression of the spring is maximum. Half m1 v1 square plus half m2 v2 square is equals to 3. Let's name this equation as equation 2. On comparing equation 1 and 2, we get half m1 u1 square plus half m2 u2 square is equals to half m1 v1 square plus half m2 v2 square. As we have already seen, let us revise. The equation 1 was half m1 u1 square plus half m2 u2 square is equals to E, where m1 is the mass of object 1, u1 is the initial velocity of object 1. Similarly, m2 is the mass of object 2 and u2 is the initial velocity of object 2. And this whole thing is equals to E. That was the total energy of the system at time t1. Similarly, total energy of the system at time t1 plus del t1 plus del t2 was equals to half m1 v1 square plus half m2 v2 square is equals to E. In both the cases, the total energy remains constant. Thereby, we have compared equation 1 and equation 2 in next slide here. So, we can say that it is not possible for kinetic energy to remain constant throughout the entire time interval, though the kinetic energy before and after collision is same. As we have seen that in previous slide, there is some change in kinetic energy happening in between in this time interval t1 plus del t1. But we have observed that there was no effect on initial and final state of the system. Thereby, it is written then, it is not possible for kinetic energy to remain constant throughout the entire time interval. Means kinetic energy may not be same, may not be constant throughout the time interval, though the kinetic energy before and after collision is same. Although the kinetic energy before the collision and after the collision would definitely be same. Now we are trying to use this exercise for better understanding of the concepts. So the question 1 says that a bullet of mass 8 grams is fired from a pistol of mass 2 kg. The recoil velocity of pistol observed to be 1.2 meter per second. Find the bullet's velocity. So we have given with the following conditions, that we have given the mass of the bullet, which is 8 grams, and the bullet is fired from a pistol of mass 2 kg. So the mass of the pistol is 2 kg. The recoil velocity of pistol observed to be 1.2 meter per second. Thereby, when this bullet of 8 grams is fired with the pistol of mass 2 kg, then the shooter receives a recoil velocity from the pistol of 1.2 meter per second. Here we are writing the given conditions of the question. Mass of the bullet, let us consider it as m1, that is 8 grams. Since we are using SI units during the numericals, thereby we need to convert 8 grams into kgs. The conversion factor we generally use for kgs to grams is 1000 grams is equals to 1 kg. So we can make out that if 1000 grams is equals to 1 kg, then 8 grams would be equals to, that would come to 0.008 kg. Similarly, mass of pistol, we are representing it by m2, and that is provided in the question as 2 kg. Velocity of bullet. We need to find the velocity of the bullet. Here it is written. That is the actual question. What's the bullet velocity? We are considering this bullet velocity as v1 and we need to find it out. Further, the recoil velocity of pistol v2. Therefore, the recoil velocity of the pistol is 1.2 meter per second. This is given in the question. Thus, going ahead with the solution, by using law of conservation of momentum, we already know the formula of conservation of momentum is m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Since the bullet and the pistol was at rest, thereby u1 and u2 is equals to 0. Let me explain that. When the bullet was not fired with the pistol, then the both bullet and pistol was at rest. Therefore, the initial velocity of the bullet must be 0, that is u1. Also, the initial velocity of the pistol must be also 0, that is u2. Thus, it is written then, since the bullet and the pistol was at rest, u1 and u2 would be equals to 0. Thus, we can say that LHS would be 0 in this equation, because when U1 and U2 will be multiplied by masses M1 and M2, they will result in 0. M1 multiplied by 0 would be 0. M2 multiplied by 0 would be 0. So 0 plus 0, that would be again 0. So this whole LHS can be written as 0. On the RHS side, let us put the values, where M1 we have already known from the previous slide that M1 is equals to 0.008 kilograms. Also M2 is equals to 2 kg and V2 is equals to 1.2 meter per second. So M1 is 0.008 kilograms into V1 plus M2 is 2 kgs and V2 we have seen it is 1.2 meter per second. Thereby, by solving this equation, we would get the velocity of bullet is equals to 300 meter per second. And so is the answer of our question. What was our question was? To find the bullet's velocity. We have denoted the velocity of bullet by V1. And here we can see V1 is equals to 300 meter per second. We are going to cover the summary. The summary that we have learned today. So we have first initially started with what is energy. Energy is the capacity to do work. Further, we get to know that energy of a moving object is defined as Ke is equals to half mv square, where Ke is kinetic energy. Further, we have learned kinetic energy of a system of objects is kinetic energy is equals to summation of half mv square, where number of objects is I. That means if there are I number of objects in the system, then the kinetic energy of the total system can be written as kinetic energy is equals to summation of half mv square of all the I objects. We have also learned that when there is a tangential component in the resultant force, the speed changes and the kinetic energy changes. We have learned this in circular motion that when there is a tangential component in the resultant force, the speed changes and the kinetic energy changes. Also, we have studied that when the resultant force is perpendicular, the speed will not change and the kinetic energy will not change. Therefore, if the resultant force is perpendicular to the velocity, then it would not be responsible for change in velocity, and so the kinetic energy will not change. We have seen kinetic energy is half mv square. So if v doesn't change, the kinetic energy would be constant, because mass is not going to change itself by any manner. Next, we can see that the work done can be written as the force acting on the object during its displacement dr. We have considered the force is Ft. Generally, we have considered the tangential force in the slides, and dr is the displacement. So work done is equals to Ft into dr, where work done can be written as dk. So change in kinetic energy is work done. K2 minus K1, we have referred to dk as earlier. The SI unit of work is joule and it is represented by capital J. Also, the unit of work done can be Newton meter, since the unit of force is Newton and the unit of displacement is meter. So the derived unit of force of work done can be written as Newton meter. We have also fortunate to learn about work energy theorem. So work energy theorem represents as work done on an object by the resultant force and the change in its kinetic energy are equal. I have represented same here. The change in kinetic energy dk is equals to the work done, where dk can be written as k2 minus k1 or kf minus ki, where kf is final kinetic energy, ki is initial kinetic energy. So the change in kinetic energy would be kf minus ki, that would be equal to work done. This has been stated by work energy theorem. Further, work done on different objects of the system by the internal forces may not be zero. In next slide, we'll see what is power. The power is rate of doing work is power. So work done per unit time can be said as power. Therefore, mathematically, it can be written as P is equals to dW by dt, where P denotes the power, dW is the work done in the unit time or in the mean time. Therefore, we have also concluded by deriving from this equation that power is equals to F into V, where F is the force and V is the velocity of the object. This has been derived from this equation only, that power is equals to work done per unit time. The SI unit of power is watt, although there is also a generalized unit that has been used for the power is horsepower. And we have studied that 1 horsepower is equals to 746 watts. We have also got to know about the potential energy. Potential energy is stored in any object or system by virtue of its position or arrangement of parts. This definition we have studied earlier. The kinetic energy of an object remains same before and after collision. Also, we got to know that in mathematical terms, conservation of mechanical energy can be expressed as work external is equals to EF minus EI. That is, if the work done by the external forces on a system, if there is some work done by the external forces on the system, then the conservation of mechanical energy can be denoted by EF minus EI, where EF is final energy of the system and EI is initial energy of the system. After learning the conservation of mechanical energy, we got an opportunity to learn conservation of momentum, where conservation of momentum can be mathematically expressed as m1u1 plus m2u2 is equals to m1v1 plus m2v2. Here, this mathematical equation states that the momentum before collision is equals to momentum after collision. Thus, u1 and u2 are the initial velocities of object 1 and 2, whereas v1 and v2 are the final velocities of object 1 and 2. Similarly, we can see m1 and m2 in our both LHS and RHS. m1 is mass of object and m2 is mass of object 2. Thus, conservation of momentum equation mathematically expressed as m1u1 plus m2u2 is equals to m1v1 plus m2v2. Here, we close our session and close our class of week. Hello everyone. So we have come today to the week 4 course of Physics Basics. In the week 4 course, we are going to study about heat, temperature and electricity. First, let us recap our previous session. Last week, we have learned about what is energy. Energy is the capacity to do work. Also, we have learned that energy of a moving object is defined as Ke is equals to half mv square, where Ke is kinetic energy, m is mass of the body, and v is the velocity of the body. We have learned few facts that when the resultant force has a tangential component, the speed changes and thus the kinetic energy changes. We always know if the speed would change, then the value of v would definitely change, and so will be the kinetic energy. So thereby this fact comes as when the resultant force has a tangential component, the speed changes and the kinetic energy changes. The another fact we have found out that when the resultant force is perpendicular, the speed will not change and the kinetic energy would not change. We got to know that if the force is acting perpendicular to the velocity, then velocity of the object will never change. And since the velocity of the object will not change, the kinetic energy would not change. We can refer to this formula for understanding this. We have also read that work done is equals to force into displacement, that is Ft into dr. We have generally termed this force as Ft due to tangential component of force, thereby Ft is tangential force. The SI unit of work done is joule, which is represented by capital J. Although work done unit can also be written as Newton meter. The unit of force is Newton, the unit of displacement is meter, thereby multiplication of Newton meter. Here we have represented work done as dk, that is change in kinetic energy. We have also learned about work energy theorem. Thereby, we have learned that work done on an object by the resultant force is equal to change in its kinetic energy. The work energy theorem can be stated as the change in kinetic energy is responsible for work done. Here we have represented the same. dk is k2 minus k1 or kf minus ki, where kf is final kinetic energy minus ki is initial kinetic energy. Thus, final kinetic energy minus initial kinetic energy, that would be equal to work done. The same is represented by work energy theorem. Also, work done on different objects of system by internal forces may not be zero. This was the another fact we have learned previously, that the work done on different objects of system by internal forces may not be zero. That means internal forces could also cause some kind of work on the system. Further, we got to know about power. Power is rate of doing work, where mathematically it can be expressed as dW by dt, that is work done per unit time. Deriving this equation, we get power is also equals to Fv, where F is the force and V is the velocity of the object. The SI unit of power is watt, and generally another unit of watt is also used, that is called as horsepower, where 1 HP, that is 1 horsepower, is equals to 746 watts. Further, we have studied potential energy. It is the energy that is stored in an object or system by virtue of its position or arrangement of parts. We have also learned the kinetic energy of an object remains same before collision and after collision, and thereby we have come to the formula of conservation of mechanical energy, that states that if the work done by the external forces on the system is equals to EF minus EI. That is, conservation of mechanical energy states that work done by the external forces would always be equals to final energy of the system minus initial energy of the system. And at last, but not the least, we have learned that mathematically conservation of momentum can be written as m1u1 plus m2u2 is equals to m1v1 plus m2v2. That is, momentum before the collision and momentum after the collision remains same, where m1 and m2 are the masses of object 1 and 2, and u1 and u2 are the initial velocities of object 1 and 2, whereas v1 and v2 are the final velocities of object 1 and 2. Next, we are going to study the table of contents of today's lecture. Today's lecture contains the following contents: hot bodies and cold bodies, heat and temperature, temperature measurement, heat transfer, electricity, current density, electric field inside a conductor, drift velocity, Ohm's law, temperature dependence of resistivity, superconductors, battery and EMF, Joule's law of heating, Faraday's law of electrolysis, Kirchhoff's law, and combination of resistors. The learning objectives of this week would be temperature and its measuring units. We are going to learn what is temperature and what are its measuring units. Also, we are going to know what is heat and how heat transfer takes place. Further, we are going to know the calculation of heat transfer on combination of conductors. That is, when the heat is transferred, then how it is calculated, and when the conductors are combined or attached with each other, how heat transfer takes place and how heat transfer can be calculated on that case. Defining electric current and current density, how electric field work inside a conductor, the dependence of Ohm's law on temperature, and last, the calculation of equivalent resistance on combination of resistors when they are connected in series and in parallel. So starting our today's lecture with hot bodies and cold bodies. Hot bodies and cold bodies. When the hands are rubbed for some time, they turn warm, isn't it? Let's take another example. When the grinding process is done on a part, the part becomes warm, or I must say it becomes hot. Let's take another example. When an aeroplane crashes, it becomes so hot that it catches fire. The next example we can take is if the same heat energy is provided to a container, then rise in temperature of a container with lesser water will be seen, and the container with more water, the temperature would not rise that much. So what we can conclude from the previous slide is that cold bodies absorb energy to become hot, as we have seen in the previous slide, that when the hands are rubbed for some time, they turn warm. Thus can be concluded, cold bodies absorb energy to become hot. The next thing that can be concluded is, hot body has more internal energy than a cold body, because those internal energy can be transferred while they are in contact. The next thing that can be concluded is, when any hot body comes in contact with a cold body, the result is the cold body warms up and the hot body cools down. That is, whenever a hot body comes in contact with the cold body warms up because there is a transfer of energy from hot body to cold body. Further, we are going to study about heat and temperature. Defining heat and temperature. So what is heat? Let's study in this slide. The non-mechanical process involves transfer of energy from a hot body to a cold body. Heat can be defined as the energy transferred from one body to another without any mechanical work involved. So, as the statement says, there will be a transfer of energy. So, heat is a kind of energy, but there will be no mechanical work involved in that. Thus, the definition of heat can be redefined as the energy transferred from one body to another without any mechanical work involved. This is because heat is a kind of energy and therefore its measuring unit is joule. What is temperature? Temperature is the measurement of hotness or coldness. It can be measured in various units like Fahrenheit, Celsius, Kelvin, or Rankine. Temperature indicates the direction in which the heat energy will flow, that is, from a higher temperature body to a lower temperature body. The next thing we are going to learn is zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two bodies A and B and A and C are in equilibrium, then body B and C are also in thermal equilibrium. Thus, all the bodies in thermal equilibrium should have same temperature if they are following the zeroth law of thermodynamics. Otherwise, a heat current will always flow from hot body to cold body, as we have learned earlier, that heat always flow from hot body to cold body. The next thing to cover today is temperature measurement. Let's take the mass of mercury in a glass bulb terminating in a long capillary tube, such that the mercury column length in the capillary tube changes with the temperature. That is, the each length corresponds to a temperature of mercury. Let me try to explain this to you again. Let a mass of mercury is placed in a long capillary tube, where the mercury column length in the capillary tube changes with temperature. Let T1 be the temperature of the ice point and T2 be the temperature of the steam point. Thus, when mercury is placed in an ice point, the column length will be L1. Similarly, when the mercury will be placed at the steam point, the column length will be L2. These are the assumptions. When the mercury will be placed in the ice point, then column length will be L1. And when the mercury will be placed in the steam point, then the column length will be L2. We are assuming a linear relation between the temperature and the length of the mercury. Thus, from the mathematics, we already know that if there is a linear relation, then the equation is like y is equals to mx plus c. This is the equation of line, and we are going to inherit this equation here also. Thus, T is equals to AL plus B, where T is the temperature, L is the length of the mercury column, and A and B are constants. Or if we refer to the mathematical equation, A is equals to m, that is the slope, and B is equals to a constant. Let's suppose y equal to mxc is equation 1. Further, change in 1 degree of temperature reflects as a change of L2 minus N1, change of L2 minus L1 divided by T2 minus T1 in the mercury column. As we have studied earlier, that change of temperature would reflect in change in mercury column. So, howsoever is the change of temperature, that is in the denominator, same will be reflected in the length of the mercury column, that is in the numerator, since both are directly related. The centigrade system assumes that ice point is at 0 degrees Celsius and steam point as 100 degrees Celsius. These are the standards that a centigrade system follows. Let L0 0 degrees Celsius in mercury column and L100 100 degrees Celsius in mercury column. This means L0 is the ice point, L100 is the steam point, and so is their temperature. 0 degrees Celsius is the temperature of the ice point, 100 degrees Celsius is the temperature of the steam point. Putting these in equation 1, that was T is equals to AL plus B, we would get the following results. When the temperature is 0 degrees Celsius, here we can put T is equals to 0. Further, we have believed that A is a slope and we are keeping this same here as well. L0 is as per the 0 degree Celsius, that is length of the mercury column obtained when it is placed at the ice point. So L will be equal to L0 plus B. Let's B be the constant as we have studied in the equation of line earlier. I repeat, 0 is the temperature at ice point, A is the slope, L is equals to L0, that is length of mercury column at 0 degree temperature, and B is constant. Thereby, by reshuffling, we get that B is equals to minus of AL0. Let's denote this equation as equation 2. Further, putting another case in this equation 1, that is equation of steam point, we will treat temperature as 100 degrees Celsius for the temperature of steam point and L equals to L100. That is, L100 is the length of mercury column when it is placed at a steam point. Rest everything remains same. A is the slope and B is the constant. By putting equation 2 in equation 3, we would get A is equals to 100 L100 minus L0. How this has came? We have just put the equation 2 in equation 3. Equation 2 was representing the value of B, that was minus of AL0. When we place that value of B, that is minus of AL0, in this equation, we must have received 100 equals to AL100 plus minus of AL0. Taking A as common and shifting it to left hand side, we would get A is equals to 100 into L100 minus L0. Let's denote this equation by equation 4 and put this equation 4 in equation 1. Thus, we would get T is equals to L minus L0 into 100 divided by L100 minus L0 degree. Another popular measuring system is Fahrenheit system, where the ice point of the Fahrenheit system is believed to be at 32 degree Fahrenheit. I hope you remember of the ice point of the degree Celsius system. That was at 0 degree Celsius. Ice point of Fahrenheit system is at 32 degree Fahrenheit. Similarly, the steam point of Fahrenheit system is at 212 degree Fahrenheit, whereas the steam point of degree Celsius system was 100 degree Celsius. Thus, by making out a relation between the Fahrenheit and centigrade system, we concluded a conversion formula to convert any unit from centigrade to Fahrenheit. That is, F is equals to 32 plus 9 by 5 into C, where F is the value of temperature in Fahrenheit and C is the value of temperature in degrees Celsius. Thus, if we put the value of temperature in degrees Celsius in right hand side and we solve this equation of right hand side, we will definitely get the temperature at Fahrenheit at the same point. The next thing we are going to study is heat transfer. There are three different methods for heat transfer: conduction, convection, and radiation. Let's start with conduction. The temperature of other end of the metal rod increases when one end of the metal rod is placed in the heater. This transfer of heat is due to the molecular collisions. This process of heat transfer is called thermal or heat conduction. Okay, so let's try to understand this using a picture. This picture perfectly denotes a rod. Let's suppose there is the one end of the rod is placed in heater. Let's suppose T1 is the temperature of the heated end and T2 is the temperature that is of the idle state. So there will be a transfer of heat from T1 to T2 and T1 would always be greater than T2. This transfer of heat happens due to the molecular collisions. Those molecules are present inside this rod, and this process of heat transfer is called thermal conduction or heat conduction. Next thing we are going to study is thermal conductivity. The thermal conductivity of a material is its ability to conduct heat. The SI unit is joule per second per meter per Kelvin. In short, it can also be written as watt per meter per Kelvin. Consider a rod of length x and cross-sectional area A. So this is the rod that we have to consider. The length of the rod is x. The cross-sectional area of the rod is A. So let the temperature of the ends of the rod is T1 and T2. This is T1, this is T2. The following assumptions are made before going ahead. The rod surface is covered well by the non-conductive material. That is, the complete surface of the rod that we can see here from between the ends, it is been completely covered by a non-conducting material. Therefore, heat transfer to the outer environment is zero. Thus, no heat can be transferred from this surface area. After reaching steady state at any given cross-section, the rod transmits equal amounts of heat per unit time. This statement indicates that when a steady state is reached in the system, there comes a time that every cross-section of the would emit equal amount of heat per unit time. That is, the heat transfer that is going to take place from T1 to T2 is going to be equal per unit time in steady state. If del Q is the heat passing through the cross section in time del T, then heat current is defined as del Q by del T. If we suppose del Q heat is transferring from a point through a cross section and it has been transferred in the time del T, then heat current is defined as del Q by del T, where the unit of heat current is watt. At steady state, heat current is proportional to area of cross section. That is, del Q by del T would be directly proportional to area. Therefore, larger will be the area, larger will be the heat current. Heat current is del Q by del T. And if smaller is the area, smaller will be the heat current, which is del Q by del T. Also, we can figure out that heat current is proportional to temperature difference, that is T1 minus T2 between the ends. If del Q by del T is directly proportional to T1 minus T2, this has been written here and this has been mathematically expressed here. Also, we can make out that heat current is inversely proportional to the length x. Del Q by del T is inversely proportional to x, that is del Q by del T is proportional to 1 by x. Converging all three equations, we can write del Q by del T is equals to K into A into T1 minus T2 upon X, where we have known del Q by del T is directly proportional to A. We have studied in the previous slide. Here, del Q by del T is directly proportional to T1 minus T2. We have studied in this here. Further, we have studied del Q by del T is inversely proportional to the length X. Here, in this equation, K is a material constant, or also called proportionality constant, or it is also known as thermal conductivity of the material. Thus, here we close our session 1. Thank you. So, let's start week 4, session 2. In session 1, we have studied about the formula del Q by del T is equals to K into A into T1 minus T2 upon X, where we have assumed that the assumptions were the rod surface is totally covered well by non-conducting material and there is no heat transfer to the environment. Now suppose if the assumptions are wrong, let there is insufficient steady state conditions in the rod while transferring of heat, and there is a non-uniform cross-sectional area. Then the equation can also be applied to a thin layer of material which is perpendicular to flow of heat. Like a thin layer could be as thin as dx. So let dx equals to small thickness along the direction of heat flow, and dt is equals to temperature difference across the layer of thickness dx. Thus, the heat current through this cross section can be written as del Q by del T is equals to minus K into A into dt by dx, where dt by dx is called the temperature gradient, and the negative sign indicates that dt by dx is negative along the direction of heat flow. Let us understand the concept using a numerical. A metal cube with a length of 20 cm is placed in a heater set at 100 degrees Celsius at one end of the cube. The temperature at the other end of the cube is 22 degrees Celsius. So the condition is there is a metal cube of length 20 cm of which its one end is placed on a heater, and the heater is set at temperature 100 degrees Celsius. Thereby, the one end of the metal cube temperature is 100 degrees Celsius, whereas the temperature of the other end is 22 degrees Celsius. Determine the heat flowing through the cube per second. Also consider the thermal conductivity of metal is equals to 385 watt per meter per degree Celsius. Here, insulation covers all other surfaces. Listing out all the given things from the question, the first thing is edge length of the metal cube is 20 cm. I have denoted it the edge length by x. Since we use SI unit, thereby 20 cm needs to be converted into meter, where we already know that 1 meter is equals to 100 centimeters. Thereby 20 centimeter is equals to 0.2 meter. Further, the given conditions of the questions are temperature at one end of the cube is 100 degrees Celsius. We have denoted it by T1. Temperature at other end of the cube is 22 degrees Celsius. We have denoted it by T2. Under the things to be considered, it is also given that the thermal conductivity of the metal is 385 watt per meter per degree Celsius. Therefore, the area of cross section of cube can be written as square of the edge length. This has come from the basic mathematics, that area of the cube is square of the edge length. Here, as we see, the edge length is 0.2 meters. So the area of cross section of cube would be square of 0.2 meters, that is 0.04 meter square. As we need to know the heat flow per second, thereby we are going to apply the formula of heat current, which is del Q by del T is equals to K into A into T1 minus T2 divided by X. Thereby, K is the thermal conductivity of the metal. A is cross-sectional area of the material. T1 is temperature at one end. T2 is temperature at the other end. X is the length of the material. So, therefore, putting the values to these equation, K is 385, A is 0.04 as we have just calculated, T1 is 100 degrees Celsius, T2 is 22 degrees Celsius, and length of the cube given is 0.2 meters. Therefore, on simplifying this equation and solving it, we get the final answer as 6006 watts. That is, the heat flow per second is 6006 watt. So is the answer of the question. Further, we are going to study about thermal conductivities of various materials. In the following table, a few materials have been given that are in general use. The table shows the thermal conductivity of aluminium is 209, thermal conductivity of brass is 109, the thermal conductivity of copper is 385, the thermal conductivity of silver is 414, the thermal conductivity of steel is 46, the thermal conductivity of water is 0.585, the thermal conductivity of transformer oil is 0.176. The thermal conductivity of air is 0.0238. The thermal conductivity of brick is 0.711. The thermal conductivity of sugarcane fiber is 0.5. The thermal conductivity of wood of oak tree is 0.146. The thermal conductivity is denoted by the letter small k, where the unit of thermal conductivity is watt per meter per Kelvin. From this table, we can also figure out which are the good conductors and which are the bad conductors of heat. Since aluminium, brass, copper, silver have higher thermal conductivity as compared to water, transformer oil, air, and brick. Therefore, these can be said as good conductors of heat, like aluminium, brass, copper, silver are good conductors of heat, whereas water, transformer oil, air, brick, sugarcane fiber, these are bad conductors of heat. Next, we are going to study about thermal resistance. Thermal resistance can be defined mathematically as R is equals to X upon Ka, where R is the denotation of thermal resistance, X is the length of the conductor, K is equals to thermal conductivity of the conductor, and capital A is equals to area of cross section of the conductor. As heat current is equals to del Q by del T, then del Q by del T is equals to K into A into T1 minus T2 upon X. Also, as we put the equation 1 in the above equation, we would get the result as del Q by del T is equals to I is equals to T1 minus T2 upon R. We have considered I is equals to del Q by del T. And as we put equation 1 here in this heat current equation, we get the result T1 minus T2 upon R. Let's try an exercise to understand this more. Analyze the thermal resistance of a copper rod with a length of 30 centimeters and a cross section of 2.25 centimeters square. Consider the thermal conductivity of the copper rod equal to 385 watt per meter per degree Celsius. So, the question says the length of the copper rod is 30 centimeter. We have write that in given as well. The given conditions are length of the copper rod is 30 centimeter and we have denoted the length by x. Also, we need to convert this 30 centimeter length into meters, which can be written as 0.3 meter. The cross-sectional area of the rod is 2.25 centimeter square as given in the question. Since we need to use the SI units, therefore we need to convert this a centimeter square thing into meter square. By applying the same conversion factor of 1 meter is equals to 100 centimeter, we would get the result of 2.25 centimeter square is equals to 0.000225 meter square. The thermal conductivity of copper is said to be considered as 385 watt per meter per degree Celsius. We have denoted it by small k. Thus, to find the thermal resistance, that is R, we have studied a formula called R equal to X upon Ka. X, K and A we have already denoted in the previous slide here in these given conditions. X is the length of the copper rod, A is the cross-sectional area of the rod, and K is thermal conductivity of copper. Thereby, R is equals to 0.3 upon 385 into 0.000225. What we have done, we have just put the numerical values to this on this equation, and on simplifying this numerical values, we get the value of thermal resistance as 3.463 per watt. So is the answer of our question. The next thing we are going to cover today is the series connection. That is, when two conductors are connected in series and heat transfer takes place between two conductors. To understand this, we need to consider a system where two conductor rods A and B are connected in series. This is a system where two conductor rods are connected in series. This is rod A and this is rod B. The free ends are kept at temperature T1 and T2, where T1 is greater than T2. As shown in the figure, the free ends, that is free end of A and free end of B, are kept at a temperature T1 and T2, where T1 is greater than T2. So the heat will flow from A to B because T1 is greater than T2. The temperature of T1 is larger than temperature of T2. Let the temperature of the junction of the two rods be T. So we have also considered the temperature at the junction of two rods be T. Thus, heat current through the rod A is I is equals to T1 minus T upon R1. How this equation has just come? We have studied the formula in the previous slides. Here we have studied I is equals to T1 minus T2 upon R, where T1 and T2 is the temperature at the ends and R is the thermal resistance of the material. Thereby, heat current through the rod A is I is equals to T1 minus T upon R1. T1 is the temperature at this open end of the rod, T is the temperature at the junction end of the rod, and R1 is the thermal conductivity of the rod A. Thus, simplifying this equation, we get T1 minus T is equals to R1 into I, as R1 is shifted to left hand side. We denote this equation as equation 1. Further, the heat current through the rod B is I is equals to T minus T2 upon R2, since T is the temperature at one end of the rod B and T2 is the temperature at the open end of the rod B. Therefore, we have written T minus T2, and R2 is the thermal resistance of the rod B. On simplifying this equation and taking R2 on the left hand side, we get the result as T minus T2 is equals to R2 into 1 into I. Let's suppose we denote this as equation 2. Thereby, on addition of equation 1 and equation 2, we get the following results. That is, T1 minus T2 is equals to R1 plus R2 into I, or We can write that I is equals to T1 minus T2 upon R1 plus R2. As a result, the two rods are equivalent to a single rod of thermal resistance. Thereby, R equivalent can be written as R1 plus R2, where R1 was the thermal resistance of rod 1, that is rod A, and R2 was thermal resistance of rod B, that is rod 2. So equivalent resistance in case of series connection would be R1 plus R2. If n number of rods are connected in series, the equivalent thermal resistance is given by R equivalent is equals to R1 plus R2 plus R3 plus dash 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 plus Rn, where Rn is the resistance of nth number of rod. The next thing we are going to learn is parallel connection. For understanding parallel connection, we have to consider a system where the conductor rods A and B are connected in parallel. Let's see in the picture. This is the system where two rods, conductor A and conductor B, are connected in parallel to each other. A temperature difference of T1 and T2 is maintained between the free ends. Thus, T1 is the temperature at one end, T2 is the temperature at the other end, and this temperature difference has been maintained at both ends. Therefore, the heat current passing through the rod A is given as IA is equals to T1 minus T2 upon R1, where IA is the heat current in particular passing from the rod A. T1 and T2 are the temperature of the ends of rod A, and R1 is the resistance of rod A, thermal resistance of rod A. So heat current of rod A is given by T1 minus T2 divided by R1. Also, the heat current passing through rod B is given by IB is equals to T1 minus T2 divided by R2. Since IB is the heat current passing through rod B, T1 and T2 is the temperatures maintained at the ends of the rod B. T1 is at this end, T2 is at this end, and R2 is the thermal resistance offered by the rod B. Thus, the total heat current flowing from the temperature T1 to T2 is I is equals to IA plus IB, where we are going to put the equations of IA and IB. Thus, in filling up the equations of IA and IB on this equation we would get following results. I is equals to T1 minus T2 upon 1 upon R equivalence, where R equivalent is equals to 1 upon R1 plus 1 upon R2. Let me explain this again. When we have to put the equation of IA first. The equation of IA can be read from the previous slide, that is T1 minus T2 upon R1. We would place this equation here, T1 minus T2 upon R1. Similarly, at IB, we would place this equation T1 minus T2 upon R2. Further, as we see, T1 minus T2 component common in both the equation, so we would take common as T1 minus T2 and let sum up 1 upon R1 plus 1 upon R2, which could be rather written as R equivalence. Therefore, I is equals to T1 minus T2 divided by R equivalence. Here, 1 upon R equivalence is equals to 1 upon R1 plus 1 upon R2, as I have mentioned here. Further, if there are n number of conductors connected in parallel, then R equivalent of the system would be 1 upon R1 plus 1 upon R2 plus dash 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 plus 1 upon Rn, where Rn would be the thermal resistance offered by the nth conductor. Let's try to understand this concept of series of conductor and parallel of conductor through an exercise. The question says, two bars of copper and steel of length 75 cm and 125 cm respectively are connected in series such that the temperature at one end of the copper is 100 degrees Celsius and temperature at other end of the steel rod is 0 degrees Celsius. Let us understand the picture first. Two rods are connected in series. This is copper rod, this is steel rod. The open end of the copper rod has a temperature of 100 degrees Celsius and the open end of the steel rod has a temperature of 0 degrees Celsius. Also it is mentioned that length of copper rod is equals to 75 centimeter, whereas the length of the steel rod is equals to 125 centimeter. Further, let's see what the question says. The diameter of both the bars are 3 centimeter. Determine the junction temperature of two rods. So, the other informations that has been provided in the question are the diameter of the rod are 3 centimeter and we have to find out the junction temperature between the two rods. Consider the thermal conductivity of copper is equals to 386 watt per meter per degree Celsius. Also to consider thermal conductivity of steel is equals to 46 watt per meter per degree Celsius. Insulate rest of the surfaces. That is, we have to consider the thermal conductivity of copper rod as 386 watt per meter per degree Celsius. The thermal conductivity of steel rod is 46 watt per meter per degree Celsius. Also, we need to consider the surface area is well insulated from the non-conducting heat transfer material. Therefore, heat would only be transferred from the copper rod to the steel rod and no other heat transfer would take place in the environment. Let's list out the given conditions first. Given the diameter of both rods, we have denoted it by D, is 3 cm. To convert 3 cm in meters, we can write it as 0.03 meters. The length of the copper rod given as 75 cm. We have denoted it by XCU, that is length of copper rod. Length of steel rod is given by 125 centimeter, that is X steel, length of steel rod. The temperature at the end of copper rod is 100 degrees Celsius. So we have written as TCU, that is temperature of copper rod. Further, the temperature at the end of steel rod is 0 degrees Celsius. We have mentioned it as T steel, that is temperature of steel rod at one end. Also, the thermal conductivity of copper rod is given as 386 watt per meter per degree Celsius, that is denoted by KCU, that is thermal conductivity of copper rod. Also, the thermal conductivity of steel rod is given as 46 watt per meter per degree Celsius. We have denoted it by K steel, that is thermal conductivity of steel rod. What we need to find is temperature at the junction of two rods. Let us denote that as phi. Heat current passes through the system is I is equals to thermal conductivity of copper into area of cross section of copper rod into temperature at one end of the copper rod minus temperature at the junction of the copper and steel rod divided by the length of the copper rod. This would be is equals to thermal conductivity of steel rod multiplied by area of cross section of steel rod multiplied by temperature at the junction of steel and copper rod minus temperature at the end of steel rod divided by length of steel rod. As we can see that A is common in both the sides and we also know from the given conditions that the diameter of both rods are same. Therefore, we can make out that the area of both rods would also be same. Thus, we are cancelling out area of cross section of copper rod and area of cross section of steel rod with each other right away. Thus, by putting values to this equation, we can write the thermal conductivity of copper rod as 386, the temperature at the one end of the copper rod as 100, the temperature we have to find out, that is the temperature at the junction, is equals to phi, divided by the length of the copper rod, that is 75, is equals to 46, that is thermal conductivity of the steel, multiplied by phi, that is the temperature at the junction point of steel and copper rod, minus temperature of steel, that is 0 degrees Celsius, divided by the length of the steel rod, that is 125 meters. By simplifying this equation, we would get the result as phi is equals to 93 degree. So this is the answer of our question, that the heat current processed through the system is 93 degrees Celsius, or the heat current at the junction point of copper rod and steel rod is found out to be 93 degree Celsius. Thus, here we close our session 2. Welcome to session 3. Today in this session we are going to study about another mode of heat transfer, which is convection. Convection is the process of transferring heat by actual motion of heated material. Like, convection is of two types, natural or free convection, and another type is forced convection. Let me remind you with the definition again. Convection is the process of transferring heat by actual motion of heated material. Let's try to understand what is natural or free convection. It is the motion of heated materials caused by density differences. Let us try to understand this by an example. When a vessel filled with water is kept on heater, then due to the conduction, the water at the bottom of the vessel gets heated. Consequently, the density of heated water decreases and thus moves upwards. Hence, heat from the bottom of the vessel transfers to the top by actual movement. Let us try to figure out this by an picture. This picture tells the same story. Here, a vessel filled with water is kept on a heater, where heater is continuously providing heat to the vessel. Thereby, the water is getting heated by the vessel through the method of conduction. Further, the heated water is getting upwards, like the bubbles located in this area, that is at the bottom of the vessels, are getting heated through the vessel through the theory of heat transfer of conduction. As they get heated, their density decreases. Thereby, it allows them to move upwards. And thereby, while they are moving upward, they carry the heat with them and thus cause the heat transfer on the other water particles through convection. This theory happens due to the change in difference of densities. Therefore, it is called as natural or free convection. The next type of convection we are going to study is forced convection. The process of forced convection is when a blower or pump forces heated material to move. In the natural or free convection, the material automatically moves itself due to the difference of density. But in the forced convection, that heated material has been given an external power of blower or pump to make it move. Examples of forced convection are when a hot air blower is switched on, the air gets heated by any heating element and the heated air is blown by the fan. Thus, the heat is carried by the air wherever it goes. That means when an air blower is switched on, the air is first gets heated inside the blower. That has been done by a separate heating element. Further, as the air gets heated, that has been blown away by the fan. The blower itself has a fan in it which blows away the heated air. This causes heated air to carry the heat with it to the atmosphere or wherever it goes. The third kind of heat transfer we have studied is radiation. When energy is emitted by a body in space, travels in the space and falls on the other body, to increase the thermal energy of receiving body. This is called radiant energy or thermal radiation or radiation. This kind of energy or radiation energy does not require any material medium for heat transfer, as we see that it can travel in space, and when it falls on the other body, it increases the temperature of the other body. The best example for the radiation is heat from the sun that travels millions of kilometers before falling on the earth. Further, the next thing we are going to cover today is electricity. What is electric current? If 1 coulomb of charge passes through an area in 1 second, then the current is 1 ampere, where coulomb is denoted by capital C, time is denoted by unit second, and second has a symbol of small s, and current is denoted by ampere with a symbol capital A. If the charge is positive, then the direction of current will be in the direction of motion. That is, the charge that is passing through an area is positive, then the direction of current would be in the direction of motion of the charge. And if the charge is negative, then the direction of current would be opposite to the direction of motion of the charge. What is current density? The amount of electric current flowing per unit cross-sectional area of the material is called current density. If a current I is uniformly distributed over an area S and is perpendicular to it, then current density can be defined as J is equals to I by S, where I and S have their usual meanings, as we have studied in the previous slide. Let's try to understand this using this example. If a current I is uniformly distributed over an area S, here the current I, here it is uniformly distributed over the area S. This is the area S, and I current is uniformly distributed, and also it is perpendicular to the area. It is actually perpendicular to the area. Therefore, the current density can be written as J is equals to I by S, where J is denoting current density. Further, if phi is the angle between the area and the direction of current, then J can be written as del I divided by del S cos phi. That is, if the cross-sectional area has an angle phi with it, then the formula of current density can be written as J is equals to del I divided by del S cos phi, where phi is the angle of the area that has been maintained between the horizontal axis and the cross-sectional area. Electric current has both direction and magnitude, but as it does not add up using triangle law of vector addition, thus it is not a vector quantity. Electric current density is a vector quantity. This point to be noted that electric current is not a vector quantity, but electric current is a scalar quantity, as the conditions for a quantity to be a vector quantity is the quantity should have both direction and magnitude, but that should also add using the triangle law of vector addition, and the electric current doesn't add up using the triangle law of vector addition. Thereby, it is a scalar quantity. Rather, electric current density is a vector quantity. Exercise time. So, the question says, if an electron beam has an aperture of 2 mm square, around 6 into 10 power 16 electrons pass through perpendicular cross-sectional area per second. Find current and current density. Consider the charge on electrons is equals to 1.6 into 10 power minus 19 coulomb. So, the given conditions are, the aperture of an electron beam is 2 mm square and around 6 into 10 power 16 electrons are passing through the perpendicular cross-sectional area per second. We need to find current and current density, and the charge on the electrons are considered to be 1.6 into 10 power minus 19 coulomb. Therefore, total charge passing through the cross-sectional area Q is equals to number of electrons into charge of electron. Look, we have to find out total charge passing through the cross-sectional area. How much charge will flow from the cross-sectional area? That is charge on one electron multiplied by the number of electrons passing through that cross-sectional area. Here, number of electrons, we are denoting it by small n. Charge of electron has been denoted by small e. Thus, total charge passing through cross-sectional area can be written as Q is equals to N into E. On putting values to these N and E, we get the total charge passing through the cross-sectional area is equals to 9.6 into 10 power minus 3 coulomb. Further, we need to find out the current. Current can be written as I is equals to Q by T. Q is the total charge passing through the area and T is the time. At what time this charge is passing through. Here we have considered time is 1 second as given in the question. Therefore, I is equals to 9.6 into 10 power minus 3 divided by 1. Thus, the current flowing through the area is 9.6 into 10 power minus 3 ampere. As charge is negative, the current will be in opposite to the direction of motion of the beam. The current density is J is equals to Is. As we have learned this formula in the previous slides, current density is denoted by small j, which is equals to I upon S. That is current upon the cross-sectional area. Here the cross-sectional area is 2 and the current we have calculated is 9.6 into 10 power minus 3 ampere. Therefore, the current density is equals to 4.8 into 10 power minus 3 ampere per meter square. So is the answer of our question. The next topic we are going to cover is electric field inside a conductor. Let's understand this by making cases. In case A, there is no electric field is applied. So, when no electric field is applied, the charge particles will be uniformly distributed in the conductor. In the case 2 or case B, on application of electric field on the conductor. When E is created on the left to the right, it causes electrons to redistribute themselves, where E is the electric field. Therefore, when electric field E is applied from left to right, it causes electrons to redistribute themselves. This drift of electrons causes an internal electric field E dash from right to left. We have seen the electric field was applied from left to right, but that caused redistribution of electrons, and that redistribution took place in the opposite direction. That redistribution caused generation of internal electric field E dash from right to left, that is opposite to the E. At this point, a steady state of positive and negative charge particles appear on the surface of the plate, where E is equals to E dash. The next thing we are going to cover is drift velocity. So, what is drift velocity? The average velocity attained by a charge particle in a material due to the application of electric field is called drift velocity. If an electron drifts a distance L in a time t, the drift velocity can be defined as Vd is equals to L by t, where Vd was the drift velocity, L is the distance covered by the electron, and t is the time in which it has traveled the distance. When there is no electric field in conductor, the drift velocity is equals to 0. That is Vd is equals to 0. When there is electric field in the conductor, Vd is constant, because as soon as the electric field is applied, the electrons will start to travel in some distance. The direction of drift velocity will be opposite to the field of electric field. The next thing we are going to cover is Ohm's law. Ohm's law states that voltage is directly proportional to the current, where resistance is the proportionality constant and depends on temperature of conductor. This is a very basic circuit to understand the Ohm's law. Let there be a circuit where voltage V is applied, causing an current I to move through the resistance R. Thereby, Ohm's law can be mathematically written as V is equals to IR. As we have seen in the previous slide, Ohm's law states that voltage is directly proportional to current. That is, if higher the current, higher will be the voltage. Lower the current, lower will be the voltage. But the proportionality constant of this equation is R. That is resistance, where resistance is equals to rho L by A. This sign is pronounced as rho. Rho L by A is equals to resistance. Let's try to understand these concepts using exercise. So, the question says, calculate the resistance of a copper wire of length 60 cm and cross-sectional area 2 mm square. Consider the resistivity of wire is equals to 1.72 into 10 power minus 8 ohm meter. Thus, listing out the given conditions first. In the solution, the length of copper wire is given as 60 centimeter. We can denote it by L. We need to convert that centimeter into meter. We need to know that 1 meter is equals to 100 centimeter. Thereby 60 centimeters is equals to 0.6 meter. The cross-sectional area of the wire A is equals to 2 mm square. When this is converted into meter scale, it can be written as 2 into 10 power minus 6 meter square. The resistivity of wire is considered to be as 1.72 into 10 power minus 8 rho meter. We have denoted resistivity of wire as rho. As we have studied, the resistance of wire R is equals to rho L by A. Therefore, we are going to find out first the resistance of wire. By putting numerical values to this equation of resistance, we can write rho as 1.72 into 10 power minus 8 multiplied by L, that is 0.6 meter, and cross-sectional area A, which is 2 into 10 power minus 6 meter square. On solving this equation, we get the result of resistance of wire is equals to 0.00516 ohms. Now we are going to study about temperature dependence of resistivity. Consider a material of following characteristics. At temperature is equals to T, the resistivity is equals to rho T. At temperature equals to T naught, the resistivity is equals to rho T naught. Let alpha is equals to temperature coefficient of resistivity of material. Given in the table are the resistivities of different material that are generally being used. Here, let the resistivity of silver be 1.47 10 power minus 8. The resistivity of copper is 1.72 into 10 power minus 8. The resistivity of gold is 2.35 into 10 power minus 8. The resistivity of aluminium is 2.63 into 10 power minus 8. The resistivity of tungsten is 5.51 into minus 8, and so on. The unit of resistivity is alpha meter, and here alpha is temperature coefficient of resistivity of material. Then for most materials following can be written. Rho T is equals to rho T naught into 1 plus alpha T minus T naught. Change of temperature causes change in length and area of material as well. And we have studied previously that R is equals to rho L by A. And we are saying that change of temperature causes change of length and change of area. So coming back to our slides, we can consider these changes as quite small and are treated as constant. Therefore, resistance would become directly proportional to rho. Hence, this equation can be also written as RT is equals to RT naught into 1 plus alpha T minus T naught. The next topic that we are going to cover is superconductors. What are superconductors? Materials for which the resistivity suddenly becomes zero below a certain temperature are called superconductors. The corresponding temperature is called as critical temperature. Let us find it out using the following graphs. Here, this is the graph of a normal metal. Since the temperature goes down, the resistivity goes down, as we can see, but it never goes to zero. This is the behavior of normal metal, that is resistivity of normal metal. Here, in the another graph, we can see as the temperature goes down, there comes a point where the superconductors believed to have resistivity of zero. The temperature at which they possess this property is called critical temperature, and so these materials are called superconductor. The usage of superconductors can be seen on building construction of strong magnets and manufacturing of ultra-fast computer switches. The next thing we are going to study is battery and EMF. Here we see batteries maintain a potential difference between their terminals. If a charge Q is taken from the terminal B to terminal A, which are distance d apart, then the work done by the battery force is equals to Fb into d. Let's try to understand this again. This is the working principle of battery. There are two terminals here. This is the first terminal. This is the second terminal. What batteries do? Batteries maintain a potential difference between their terminals. If a charge Q is taken from terminal B to terminal A, which are d distance apart. Here we can see a charge Q has been taken from terminal B to terminal A. The distance between the terminal is d. The force acting for taking the charge from B to A is Fb. Then the work done by the battery force is equals to Fb into d. The work done per unit charge can be written as E is equals to work done upon Q. That is, Q is the unit charge. Work done we have already studied in the previous equation, that is equals to Fb into d. Therefore, we can write work done per unit charge is equals to E is equals to Fb into d upon Q. This is called electromotive force of the battery, or in short it is said as EMF. As observed, EMF is not actually a force, but it is actually called as work done per charge. The points to be noted here are potential difference and EMF are two different quantities. As we saw, there was a potential difference between the terminal B and terminal A, which caused an electron to move from terminal B to terminal A using a force Fb, whereas EMF has been defined in the previous slide as work done per unit charge. EMF, that is electromotive force, are non-electrostatic in nature. The potential difference originates from electrostatic field created by the charges accumulated on terminals of battery. The EMF of the battery is equal to potential difference between its terminals when the terminals are not connected externally. Here we close this session. Thank you. Let's get started with our last session. The last session we will be starting by studying Joule's law of heating. When an electric current I passes through the resistor having the potential difference V between its both ends, the thermal energy of the resistor increases. The work done by the electric field during that time, that is at time equal to T, is work done is equals to potential difference into charge, where potential difference can be denoted by capital V and charge is denoted by IT. Further, work done is equals to IR into IT. From Ohm's law, we know that V can be written as IR. Further, simplifying this equation, we can write that work done can be written as I square RT. This work is converted into thermal energy due to the collisions with the lattice, also referred as the heat produced in the resistor and is denoted by capital H or capital U. What's James Prescott studied? The name of the scientist was James Prescott Joule. He studied that a resistor's heat production in a given period of time is proportional to its current squared. That is, heat is directly proportional to square of the current. That is, H is directly proportional to I square. The another thing he noted is the heat produced in a given resistor by a given current is proportional to time for which the current exists in it. That is, heat is also directly proportional to time. The third thing he studied is the heat produced in a resistor by a given current in a given time is proportional to its resistance. That is, H is also directly proportional to R, that is resistance. Conclusively, we can say that H is equals to I square RT. Now we try to understand this concept using the exercise. A resistor produces thermal energy of 500 joules in 10 seconds. When a 2 ampere current is passed, find its resistance. So we need to find the resistance of the resistor. The next part of the question asks us if the current is increased to 5 ampere. Previously it was 2 ampere. Now if the current is increased to 5 ampere, what will be the energy developed in 10 seconds? So the time limit is same, 10 seconds in both the conditions. But now the current has been increased from 2 ampere to 5 ampere. Let's get into the solutions and write the given situations first. The given conditions are as follows. Thermal energy of the resistor is given as 500 joule and we denote it by capital H. The current supplied to a resistor is 2 ampere. We denote it by I. Time for which current is supplied is 10 seconds. We denote it by small t. As from the Joule's law formula that H is equals to I square RT. Thus, putting the values to this equation, we can write 500 in the place of H, since this is the thermal energy of the resistor. I square is 2 square. R we need to find out, that is the resistance. Time limit is 10 seconds, that has been provided in the question. On solving this equation, we would get the value of resistance as 12.5 ohms. Further, the next part of the question asks us calculated resistance of the resistor R is 12.5 ohms. Current supplied to resistor I equal to 5 ampere. Time for which the current supplied is 10 seconds. The question asks us what is the heat generated if current is changed to 5 ampere. Thus, using the same formula, the Joule's heat formula states that H is equals to I square RT. Here, by putting values to this equation, we can write it as H is equals to 5 square into 12.5 into 10. Thus, solving this mathematical calculation, we get the answer as H is equals to 3125 joules. So is the answer of our question. The next thing we are going to study is Faraday's law of electrolysis. The Faraday's law states that the mass of a substance liberated at an electrode is proportional to the charge passing through the electrolyte. The same thing can be written in a mathematical manner as following. M is the mass of the substance is directly proportional to the charge Q which is flowing in the electrolyte. This can be written as M is equals to ZQ, where Z is a proportionality constant here. Also, Z is a constant for substance being liberated, also called as electrochemical equivalent. Its SI unit is kg per coulomb. If an electric current I is passed through an electrolyte for a time t, the amount of charge passed is equals to Q is equals to IT. Putting this in equation 1, we can write as M is equals to Z into IT, as we have replaced Q by IT. This was our equation 1. Thus, it became M is equals to Z into IT. Understanding this using the exercise, the question says, calculate the time required to deposit 0.9 grams of chromium when 0.6 ampere current is supplied. Consider ECE is equals to 0.00018 gram per coulomb. Thus, using the Faraday's electrolyte formula, as we know, M is equals to Z into IT, where M is given as 0.9 grams. ECE is also given in grams, therefore we don't need to change the units. It is 0.00018 and I is 0.6 ampere as mentioned in the question. We need to find out the time. Thus, simplifying this equation, we get the result of time as 8333 seconds, and if we generalize it, we can say that it is around 2.31 hours. So, the answer of the question is 2.31 hours is required to deposit 0.9 grams of chromium when 0.6 ampere of current is supplied. The next thing we are going to study is Kirchhoff's law. Kirchhoff's law is divided into two things. The first is the junction law. The sum of all currents directed towards a point in a circuit is equal to the sum of all current directed away from the circuit. Here we can see there are 4 resistors that is causing a complete circuit. So the junction law states that the sum of all currents directed towards a point in a circuit, like all currents directed towards a point, the center point, let's consider a center point in a circuit, is equal to the sum of all currents directed away from the circuit. Therefore, it says that if I1 and I2 are the two currents that are pointing towards the center and I3 and I4 are the two currents directing away from the center, then the sum of I1 plus I2 would be is equals to I3 plus I4. Otherwise, the algebraic sum of all currents directed towards a point is 0. Also, it is saying that if all the currents are pointing towards the center, then the algebraic sum of all the currents would be 0. Referring to the circuit for junction law, as I said, I1 and I2 would be equal to I3 and I4. If we mention that I1 and I2 are possessing current towards the center and I3 and I4 possessing current away from the center. This can also be understood by shifting the RHS to the LHS, that is I1 plus I2 plus negative of I3 plus negative of I4 is equals to 0, which we have studied the second point in the previous slide. This one, the algebraic sum of all currents directed towards a point is 0. The second part of Kirchhoff's law is the loop's law. The loop's law states that the algebraic sum of all the potential differences along a closed loop in a circuit is 0. To use such a rule, the basic things are kept in mind. Those are: start from any point on the loop, go along the loop either clockwise or anti-clockwise, reach at the same point after completing the whole loop. To use such a rule, we also need to consider the following points. Any potential drop encountered is taken as positive. Any potential rise encountered is taken as negative. The net sum of all these forces shall be 0. Things to be noted: it can be concluded that electrostatic force is conservative. Work done by it in a closed loop path is 0. Thus, it is mentioning that since the work done in the complete closed loop path is 0, therefore electrostatic force can be considered as conservative forces. The next thing we are going to study is about combination of resistors. Let's start with series combination. Two or more resistors are said to be in series if the same current passes through all the resistors. Like we see in the figure, two or more resistors, there are three resistors here, are said to be in series if the same current passes through the all resistors. Here in the circuit we see the same current passing through all the resistors. The current is I. It is passing through R1, then it is passing to R2, then it is passing through R3, and thus getting back to the battery. Consider a circuit with resistors R1, R2 and R3 connected in a series and is connected to the battery of volt V. So this is a battery of volt V. Using Kirchhoff's law, we can say that IR1 plus IR2 plus IR3 minus V is equals to 0. As we have studied Kirchhoff's law before, that the voltage can be taken as negative if there is a potential rise, and the rest things are IR1 plus IR2 plus IR3. So the equation becomes IR1 plus IR2 plus IR3 minus V is equals to 0. We write it this as V on the right hand side, and taking I as common, we also take I on the right hand side, which becomes V by I is equals to R1 plus R2 plus R3. I just mentioned that V by I is equals to R equivalent. How? We have studied in an Ohm's law that V by R is equals to V by I is equals to R. Thus the equivalent resistance is R equivalent is equals to R1 plus R2 plus R3. This argument can be extended till any number of resistors in the series. Thereby, R equivalent can also be written as R1 plus R2 plus dash 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 plus Rn, where Rn is the resistance offered by the nth resistor of the circuit. The next thing we are going to learn is parallel combination. Two or more resistors are said to be connected in parallel if same potential difference exists across all the resistors. Consider a circuit with the resistors R1, R2 and R3 connected in parallel and is connected to the battery of volt V. Let's see in the circuit, there are three resistors R1, R2 and R3. They are considered to be in parallel as if the same potential difference exists across all resistors. As we can see in the circuit, same potential difference of V exists for all the resistors. Although we can also see there is the division in current I, where I1 is the current for R1, I2 is the current for R2, and I3 is the current for R3. Thus, using Kirchhoff's law, I is equals to I1 plus I2 plus I3. Let us give this equation a name as equation 1. Using Ohm's law, we can write it as I1 is equals to V by R1, I2 is equals to V by R2, and I3 is equals to V by R3. Putting these in equation 1, we can write as I is equals to, we are taking V as a common, as V would be common for all the three resistors since this is a parallel combination circuit. Therefore, taking V as common, we can write 1 upon R1 plus 1 upon R2 plus 1 upon R3. Therefore, 1 upon R equivalent can be written as 1 upon R1 plus 1 upon R2 plus 1 upon R3. Above can be extended till any number of resistors in parallel, like 1 upon R equivalent can be equal to 1 upon R1 plus 1 upon R2 plus dash 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 plus 1 upon Rn, where Rn is the resistance offered by the nth resistor of the circuit that has been attached in parallel combination. Let's try to understand both series and combination circuits using an exercise. So here's the question. Find the equivalent resistance of the circuit as shown in figure between points A and B. So we have to consider this diagram, circuit diagram. So this is point A, this is point B. We need to find out the equivalent resistance between the point A and point B. We can see a resistor of 20 ohms in the parallel combination with the resistor of 30 ohms. Also, we see that 2.5 ohms is the resistor in series with the equivalence resistors of this parallel combination. Thus, coming into the solution, resistors in parallel are 20 ohm resistor and 30 ohm resistor. Let R dash be the equivalent resistor of parallel combination. Let's say the equivalent resistor name could be as R dash, where I have already considered 1 upon R equivalence is R dash. Thus, R dash equals to 1 by 20 plus 1 by 30. We can write as 1 upon R1 plus 1 upon R2 is equals to 1 upon R equivalence is equals to R dash. I have considered this equation and we have learned this in the previous slides. Here we have seen 1 upon R equivalence is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. I have considered 1 upon R equivalence itself as an R dash. Therefore, I have directly applied the formula R dash is equals to 1 upon R1 plus 1 upon R2, and we don't have the third resistor in parallel. Therefore, 1 upon R1 plus 1 upon R2 only. Putting values to that equation, we can write R1 as 20 ohms, R2 as 30 ohms. Thus, 1 upon 20 plus 1 upon 30 can be equal to 30 into 20 divided by 30 plus 20. Let's see how it came. As we have to sum up this equation, we have to take first the LCM of 30 and 20. So better, I have directly multiplied 30 with the 20 divided by 30 plus 20, which is equals to, in the numerator we used to sum up 30 plus 20. Okay, 30 plus 20 divided by 30 into 20. That's how we used to do. Since we have to directly find the R dash, it is 30 into 20 divided by 30 plus 20, and thus giving the result 12 ohms. Further, we can see this R dash resistance is connected in series with 2.5 ohm resistor. Therefore, the calculated resistance of R dash now going to be in the series connection with 2.5 ohm. We have calculated R dash as 12 ohms. We also know that the R equivalence for the series circuit is R1 plus R2, as we have seen in the previous slides. Here we have seen R equivalent is equals to R1 plus R2 plus R3. In our case of question, we don't have R3. R1 is the equivalent resistance of the parallel combination. We have named it as R dash, and R2 is equals to the resistance that has been given in the circuit as 2.5 ohms here. Therefore, R equivalent of the complete circuit is equals to R dash plus 2.5, where R dash we have calculated 12 ohms plus 2.5 ohms, that would result in 14.5 ohms. So this would be the answer to a question, that was to find out the equivalent resistance between the point A and point B of the circuit. Now we are going to summarize the complete things that we have studied today. So this week we have started from heat. What was heat? Heat can be defined as the energy transferred from one body to another without any mechanical work involved. Next thing we have studied after heat is temperature. Temperature is the measure of hotness or coldness and can be measured in Fahrenheit, Celsius, Kelvin, and Rankine cycle. As Celsius and Kelvin are the similar units, similar is the case with Fahrenheit and Rankine cycle, although all the units result in measuring temperature. The next thing we have studied is heat current will always flow from hot body to cold body. As the hot body have greater internal energy, thus the heat current will always flow from hot body to cold body. We have also studied that heat transfer can be taken place by only three types. The first type through which the heat transfer could take place is conduction, where conduction heat transfer is due to the molecular collisions. The next kind of heat transfer that could happen is due to the convection. Convection is the process of transferring heat by actual motion of heated material. That is, when the material gets heated, it itself moves to the another part of the cold body to transfer its heat. This is called the process of convection. The third type of heat transfer that could happen is the radiation, where we can say that radiation does not require any material medium for heat transfer. Further, we have learned about the electric current. Transfer of charge from one side of an area to the other causes electric current through that area. If the moving charges are positive, then current is in the direction of the motion of the charges. Similarly, the moving charges are negative, then current is in the opposite direction of the motion of charges. We have also studied that the amount of electric current flowing per unit cross-sectional area of the material is called as current density, where J is and can be equal to del I upon del S cos phi. If the cross-sectional area is in perpendicular direction, then the current density would directly be J is equals to del I upon del S. On application of electric field, positive and negative charge particles redistribute themselves closer to surface of plate. We have seen this in electrical field concept, that when an electric field is applied, which are uniformly distributed before, try to reshuffle themselves or redistribute themselves and they get closer to the surface of the plate. This movement of particles caused drift velocity in the particles. There comes the drift velocity. The average velocity attained by a charged particle in a material due to the electric field is called drift velocity. Just now in last point we have seen when an electric field is applied, the particles redistribute themselves. During the redistribution, they attain some velocity in them. Thus, that velocity is called drift velocity, represented by Vd, that is equals to L by T, where L is the distance covered by the particles while redistributing themselves at time t. Therefore, drift velocity is equals to L by T. Further, we have also studied Ohm's law. Ohm's law states that voltage is directly proportional to current, where resistance is the proportionality constant and depends on the temperature of conductor. As we see, voltage is directly proportional to current, where resistance is the proportionality constant. Thus, V is equals to IR. Moreover, the resistance is very much dependent on the temperature of the conductor. Also, we can write R is equals to rho L by A, where rho is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area of the conductor. Here, we also have read temperature dependency of resistivity. it can be written as RT is equals to RT naught into 1 plus alpha T minus T naught. Here, the factor L by A, which has been changed due to the temperature, has been considered negligible. Thereby, RT can be directly related to RT naught into 1 plus alpha T minus T naught. Further, we have studied materials for which the resistivity suddenly becomes zero below a certain temperature are called superconductors, where the temperature at which resistivity suddenly becomes zero is the critical temperature. We also got an opportunity to learn about the batteries. A battery is a device which maintains a potential difference between its two terminals, where also EMF of the battery can be defined as the work done per unit charge. Thereby, it can be written as EMF can be written as E, work done per unit charge can be written as W by Q. W is work done, Q is the charge. Also, work done can be elaborated as FB into D, which is force into the distance covered by the charge per unit charge. Thus, the EMF of the battery can be defined as E is equals to FP into D divided by Q. Further, we got to know about Joule's law of heating as well. The Joule's law of heating can be summarized by a single formula, that is H is equals to I square RT, where I is the current, R is the resistance, and T is the time. Further, we got to know about Faraday's law of electrolysis. The mass of a substance liberated at an electrode is proportional to the charge passing through the electrolyte. This was Faraday's law of electrolysis. The next things we have learned was Kirchhoff's law, which was divided into two, the junction law and the loops law. The junction law states that the algebraic sum of all the currents directed towards a point is zero, whereas the loops law states that the algebraic sum of all the potential differences along a closed loop in a circuit is zero. The last things we have learned about the combination of resistors, and we got to see that there were two kinds of combinations that are possible in resistors. The first is the series combination of resistors, where we have seen R equivalent can be written as R1 plus R2 plus R3 plus dash 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 plus Rn, where Rn is the resistance offered by the nth resistor of the series combination of the resistance of the circuit. Further, at the last but not the least, we have studied the parallel combination of resistors and have concluded that 1 upon R equivalent can be equal to 1 upon R1 plus 1 upon R2 plus dash 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 to 1 upon Rn, where Rn is the resistance offered by the nth resistor of the parallel combination circuit. Here we sum up our last session of this course. I should say thank you so much.